Good evening, y'all. Welcome back to another Sunday night Fundamentals of Electronics and Arduino Programming stream. I'm Jeff. It's good to see you all again on this lovely Sunday night. Hi, Chris. Thank you for the brief pause as I got started tonight. So always last-minute mic issues, and I'm watching myself clip, and it's all going great as usual on a Sunday night. And get our little timer started here. As always, we're going to wait just a few minutes to let stragglers catch up before we dive into the nerdy things that we have planned for today. Hi. Which for today, as you can tell from the title of all the things, and I remember to change the number of the episode tonight, which is always a good sign, we're going to talk about how to get signals from one place to another place over a wire. Last week we talked about a method of doing it wirelessly, and we looked at the Radiohead library and how to do that. Hey, Lee, how's it going? And this week we're going to talk about how to do that wiredly, how to get signals from one place to another over a wire using particularly RS485 and DMX, which are related to each other, as we'll see in a little bit. I'm going to talk about a few other things. That's the thrust of tonight. This is not just me showing off. It is DMX powered. It's RS485 controlled, but it's a little bit showing off. I'm super proud of how this little light came out so far. Like it is still definitely beta. Like it has some ways to go before it's finalized and can be assembled. Hey Nate, how's it going? But yeah, it turned out really good. And now it's just a matter of like figuring out how to figure out how to make more of them, make them more reliable, make them more consistent, make them easier to assemble. So I think by the end of the night we'll have the ability built up on an Arduino to like actually control a little lighting fixture like this directly from some Arduino code, or a lighting fixture like this, or like a full-sized, Mac Encore, or some other crazy DMX controlled fixture. There was one we were looking at. I forget. I think it was Alec Thorne and I were looking at one, a DMX fixture that takes like 512 parameters in what they called insane mode, which is just insane. And it doesn't seem insane to you yet if you don't have the background. Like I know there's a lot of lighting nerds out there tonight, but if you're not a lighting nerd, by the time we get to the end of this, you'll know why that's an absurd thing. As always, no pressure to drink anything you don't want to, but tonight I am drinking a Zombie Dust from Three Floyds Brewery here in the Midwest. A really tasty, bitter IPA kind of thing. This actually, it's in a glass because, and it's about to be in this glass, because we ordered a portable growler, a disposable growler from a local brewery here, a local bar, along with some really good pub burgers. So I'm just killing our plastic growler of Zombie Dust for this evening's stream. See if I can do good this week about remembering to mute myself when I drink, because I'm sure I'm still playing with how the microphone works. But I'm sure it's not super pleasant to hear gulping super up close. Chris says, when do you play the commercial for the light? So I don't know that I will never really plan on selling these, but someday, like, you can, when the control boards are up and like consistent enough that they're on Tindy, yeah, I'm gonna be plugging it if these are still going on. Because I've been working on this light on and off for a long time now, and so who knows where it'll actually end up or how long we'll continue working on it. But yeah, it's been super fun. Why don't we? I see our timer has run out. Let me turn that guy off and get him out of the way real quick, and we'll dive into talking about the main thrust of our things tonight. Let's see, what are y'all drinking out there this evening? I should ask. Again, no pressure. Like, if water is what you're drinking, that's totally fine. Like, this is, I know, alcohol pressure is a real thing in our world today. No pressure, but if you're not, you should hydrate. Get the light out of the way. Get the cable out of the way. These cables, I know I'm just delaying now, but like I know that like this is a super cheap cable. You're meant to control RGB LED tape with these, but I use them for this light because they're super duper cheap. Like this cable was like $1.50 with 2-day shipping and like 50 cents from overseas on this low boat. So like cheap is good. Ooh, Riverland's Acid Rainbow Stone Fruit. Chris, I'm guessing that that's some kind of alcoholic beverage and not like a brand of LSD, but it could be either, and it sounds delicious either way. It's fine. I'll just get started. Let's talk about what we're going to talk about tonight. Let's see if we're over here. All is good. Yeah. So after last week, we looked at how to get signals from one Arduino to another wirelessly. This week, I want to look at how we're going to get them from one place to another in a wired fashion. And this should go without saying. But if you ever, have the choice between, running a wire or doing something wirelessly, the wired thing is gonna be more reliable. There are certainly lots of situations where the wireless option is going to be more flexible, right? Especially if you have battery power and a wireless signal between two things. Now your remote unit, whatever it is, can be moved around from place to place, and that's great. But if what you want is reliability, running a wire will almost certainly be the more reliable way to go, and that's why you see wired communications used in everything from theatrical lighting control to sound to automation control in factories. Like if you run a wire, the physical medium is going to be fairly reliable. Ooh, Nate says, threw an old peach IPA from Green Flash Brewing Co. in the freezer. Ooh, that's going to be super good. It's nice and cold on a hot summer day. That sounds great. So let's talk about wired things. Also, let me know. I know I mess with the mic every time, but if the sound is weird, let me know and we'll tweak it or fix it. I know there's probably some popping because it's right here and the windscreen's not very good. So we'll keep working on things. So let's talk about. I'm gonna move this. Let's talk about one really common mode of wired communication and some other things we're gonna look at tonight. There we go. Oops, I didn't change my mouse again, you guys. I know this is like the third time we've done this, but now I know right where this option is. Change the pointer to normal and highlighted and apply. And there's our, see, when this happened back in like episode 3, which feels like it was about 17 centuries ago, you remember how long it took me to figure out how to change the mouse? We're pros now. Today we're going to talk about RS485, which is a physical protocol for communicating between two things or wiring two things together. We're going to talk about network topologies associated with that and network topologies in general. So what structure and what order things are hooked together. We're going to talk a little bit about signaling versus addressing and what those two things mean. We're going to talk about DMX, which is built on top of RS485 as a particular signaling protocol to communicate between some things. And we're going to dip our toes into the OSI model, which is a structured way of thinking about communication protocols. So let's start. I really liked last time we started with a demo as opposed to doing 40 minutes of theory. So let's do a demo that I'm not actually sure we ever did, like back in week 2 when we talked about serial communication. So this will be the circuit. It's 2 Arduinos with the TX line of 1 or pin 1, digital pin 1, hooked up to the RX line on the other Arduino. So let me get that plugged in real quick, and then we'll take a quick peek at the code, which will be nothing fancy. So here, I'll probably zoom out a little bit here. And as always, ask questions, ask comments, share things that you've like, oh, I tried this thing, and it didn't work or did work, or I heard this and I don't understand, because that's what tonight is all about. So I have my, let's get rid of that screen there. There we go. So I have my 2 Arduinos here, and I've written on them which COM ports they seem to be populating on my computer, just so I try and upload the code to the right place. I'm going to plug them both in. Plug in that one. I heard a little bloop-a-doop in my ears that tells me that it's connected, and that one too. So let's upload some code, and then we'll hook the 2 of them together. Chris says 40 minutes of Jeff theory. I feel like we had some nights where 40 minutes was like the full 90 minutes of the night before we actually did anything. So let's do a thing. So over on the computer here, and I should say, because I should say every week, I mean, those of you I'm seeing in the chat, you already know this, but all of the slides, all of the code, and all the links for tonight's explanations are on the website, which is over here, jeff.glash/electronicsbash. If following along on the slides on the screen is not super helpful, hi Brian Q. You can follow along there. You can also download all this code or look through the code as we go along. Just because I know looking at somebody else scrolling through text is not always the most parsable, if that makes sense. So the code we're going to look at first here is a couple of pieces of code, right? Because we have a couple of Arduinos to upload it to. This will be the basic receive and the basic send code. So let's look at the basic send code first. Let's zoom in a little bit here. Here we go. It's not going to be anything terribly surprising. I just don't think we've ever done this demo before. So we're going to define a pin to which an LED is attached and a value that we'll hold on to. This is that uint8_t type that we looked at last week? Last week it must have been. Wow, that feels like about 100 years ago too. That just means a byte, 8-bit value that will start off as 0. We'll start up our serial communication protocol. We'll make sure that our LED pin, and we're going to use our built-in LED as well. Those are both configured as outputs using the pin mode command. And then our loop is going to be really simple. Every time we go through the loop, we're going to increase our value by 10, and then take it modulo 255. So we're going to increase by 10, and then take the remainder when we divide by 255. Basically, when this value goes over 255, we'll loop back around to 0 and start again. Every time we do on this is on the transmitter, remember, this is our sending code. We're going to set our the analog value of the output on our LED pin to the value that we're tracking. So this is going to fade up from 0 to 255 and then loop around back to 0 again. Just fade up, fade up, fade up, and so on. We're also going to write that value to the serial port, and then we'll delay for 100 milliseconds. And then just so we can see, that things are happening, I got this command here. If millis, which you remember is the number of milliseconds since the program started running, modulo 1000 is greater than 900. So basically, if we're in the last 100 milliseconds of every second, we will digital write the LED built-in pin highs. We'll turn on that built-in LED. Otherwise, we'll turn it off low. So basically, for 100 milliseconds out of every second, that light will turn on. Otherwise, it will turn off. This is going to give us like a little heartbeat just so we can see that things are happening. So let's go ahead and upload that code. That goes to COM11. Make sure that we're set to Arduino Uno, and we'll upload. And we'll come to the table. This is already running some code from another experiment I was doing, so we'll see there. But we should see that that LED starts at 0, and then slowly fades up to max, and then starts at 0 and fades up to max again. So nothing terribly novel there now, right? Let's look at the receive code. The receive code, and this is the basic receive demo if you're playing along at home, again, has an LED attached to it, this time on pin 6. It's arbitrary. I just wanted them to be on different pins. Probably would help to remember which was which when I was setting up these demos. We're going to start our serial console on this side as well. And I'm going to do a thing called serial.setTimeout, which we haven't looked at before. We actually don't need here, but it basically says if you're looking for a value that is more than 1 byte long, which we may in some later demos, it's going to wait a maximum amount of time from the time it receives the first byte to when it gives up and just says, hey, I actually don't have anything. So if you were sending a long integer over your serial port, if you were expecting to receive a long integer, which we talked about last week is 4 bytes long, this is going to say, okay, from the time I receive that first byte, I'm going to, hey, something's coming in. I will pause probably in my serial.available part of my code, assuming more bytes are coming. But if I take more than 200 milliseconds, then I must not have been getting the long that I thought. I've seen less than 4 bytes. They don't make up a long integer. I'm giving up and carrying on. So that's all this set timeout function is here. And once again, we've got an LED pin that'll be our output, and the built-in LED will also be an output. And then our loop code is really simple as well. Again, nothing terribly novel. So while serial.available, and you remember back from our serial lessons in week 2 at the end of March, which is crazy, that this function returns true when there is something waiting on the receive side of the serial port to come into the Arduino. So this is basically saying, hey, if there's anything, if anyone sent a message to me on my serial port, I'm going to want to do something with it. If there's nothing available, carry on, do something else. And you'll see I have that same heartbeat code down here. So for the last 100 milliseconds of every second, that built-in LED turns on again, just so we can see something's happening, even if we're not passing serial back and forth. And then in our receive code here, I'm going to take in a value from serial.read, which just pulls a value out of the serial incoming buffer, right? So because we had serial.available was true in this while statement, we know we have bytes waiting for us. So read them into this value, write them to the LED pin, right? So since we're only sending values between 0 and 255, we'll just write that value, that in value, directly to the LED pin. And then I'm going to actually have it print itself to its own serial port as well, right? This serial.flush was an experiment I was doing earlier. That's changed a little bit in Arduino 1.0. So never mind about that. So let's upload this code, and hopefully you can sort of roughly see. So the sending code was sending out values between 0 and 255, looping back to the beginning. The receiver is taking in values and writing them to its LED. So when we connect the two of them together, and it looks like we're done uploading, what I'm going to do is take this pin from the TX pin, and I'm going to attach it to the RX pin, which is this white cable here of the receiver. Chris says, why did it look like the LED on the transmitter is fading up and not blinking? Shouldn't it? So good clarification, Chris. So the transmitter is doing 2 separate things. So it's increasing this value modulo 255. It's writing that, doing an analog write to pin 11 in this case to fade up that LED. and then separately, it's blinking the built-in LED. And mostly why I wanted to do that, if we look at the table here, if I don't connect to the receiver, we can see, of course, that the receiver is not receiving any signals, so that LED that it's attached to is not changing. I wanted a way to see that, like, hey, the Arduino is still running. It's still doing its loop. It's still doing things. This is just not changing. It's not until that I start feeding serial commands into this Arduino by connecting the TX line, it's plugged into TX up here, into the RX line of this Arduino, that the two should basically move in lockstep, right? Because this is generating a value between 0 and 255 and doing an analog here. Also spitting that value over to the other Arduino, which is doing an analog right here, right? So a really simple way of passing messages between two Arduinos. As I was setting up this week, I was like, I don't think we actually ever did like the really basic way that you get two things to talk to each other over a wire. It's just as simple as connect a TX to an RX. You can also do both of these at the same time, right? You could set up a TX to an RX over here. You would have to do some work in that case to, you know, figure out which way you were communicating at any given point, right? So you'd need on both sides of in both sets of your code, your transceiver code, basically saying, you know, transmit this, and then if serial.available, do this, and you could pass messages back and forth that way. There's some examples in the serial examples in the Arduino IDE, so remember those are up in the file menu under examples, under communication. I want to say serial call response. Let's see if that's what I'm thinking of, just in case you wanted to dig into an example of this, which basically says if serial.available, serial.read, and then serial.write. So it takes in some values and spits back some values, just so as an example of one way you might structure that, if that makes sense. Question so far? That's a pretty straightforward demo, but like I really can't believe we haven't done it yet. It's gonna kind of be the foundational demo of everything that we do tonight, because. So this is a perfectly valid way to get two microprocessors, two Arduinos to talk to each other. Currently, they're communicating over a wire distance of about, I don't know, 8 inches, a couple of 4-inch-ish wires, maybe a foot. And this method would probably work up to, well, it would depend on the speed of the serial signal. So in my code right now, I sort of arbitrarily picked this 9800 baud as our speed. If we stretch this wire out at 9600 baud, we might get, I don't know, 50 feet-ish, 25 feet, like that. Really, this communication protocol, this UART-based protocol, and remember, UART is Universal Asynchronous Receiver Transmitter. This TTL level, 5-volt UART transmitter is really meant to communicate between things that are close to each other, in the sense of like in the same panel, on the same circuit board, maybe a few feet away in the same device. They're really not meant for communicating between things that are, you know, that are separated, right? So if you think about, just to take an example, like a giant tank of mineral oil that was being sloshed about by a big wave pushing arm, for example, something that's come up in my life in the past year, and Brian's life as well. If there were sensors or components in the control box, as big NEMA control boxes mounted underneath that, I would, and I saw they were communicating via UART, fine. You know, a few feet, not bad. Even if there was a sensor inside the tank, probably fine. You know, 12 feet is not an extreme distance, especially for low speed. When you start getting into higher speeds, your distance starts to get shorter because your driver basically has less time to pull that whole line or push that whole line up or down to a signal level. So this will kind of be a general truth of tonight, is the faster your signal rate, the less distance you can reliably go with it. I'm hoping that sort of intuitively makes sense. You can think of it like, you know, going back to the water analogy of electricity, if your transmitter is responsible for changing the voltage on an electrical line from 0 volts to 5 volts and back, you can think of it like if the wire is like a tank of water, your transmitter has to fill that tank up to a certain level to be 5 volts and open a valve and drain it all out to get it down to 0 volts. Now, of course, it's happening much faster than water would, but the longer your line, the bigger your tank. And so the less, the more force your pump or your valve would have to apply in order to make the same thing happen in an amount of time. And, you know, trying to fill and empty that tank, say, once a second is going to be a lot easier than filling and emptying it millions of times a second. So that'll kind of be a theme tonight is, these things don't have necessarily a hard and fast distance limit. It's going to be based on how fast the faster you go, the shorter distance you can go. Additionally, how noisy your environment is. And that is actually one of the big problems with a UART-based communication scheme, is that any noise, any electrical noise that's coupling into these wires, any, nearby cell phones that, might be wandering by in a child's pocket, or noise from your radio or your computer, or any of the other thousands of things that generate electrical noise in our lives, that is going to emit some radio frequency waves, and low frequency and high frequency is going to couple into these cables and cause the electrical level in them to jitter just a little bit. And at a certain point, that jitter is going to be enough that you will no longer have a reliable sense at the receiving end, whether you see, 5 volts as a 1 or 0 volts as you might be in that no man's land in the middle there where we can't really tell what we're seeing. Oh, Palmer. Hi, Palmer. How are you? Palmer, what are you drinking? Palmer asks, what's the acceptable max-min baud range of the serial command? So the serial command in the Arduino IDE has some very specific allowed values. You can see all of them. The easiest way is if you open up your serial terminal, you can see mine is, I'm just doing this weird resizing thing again. Why is that? Get out of there. Get out of there. This happened last week too, remember that? I don't know what causes this, where it won't be anything less than the full height of the screen. Bring it to the other window? No, I don't know what's going on. Is it because I already have values? I don't know. In any case, if you open up your serial monitor and come to the bottom when it lets you... Oh, there we go. You can't see that. Let's get me out of the way there. I guess I don't have just a computer button. That's unfortunate. Well, down on the bottom right here behind me, where you select your baud rate in the serial monitor, it will list for you all of the acceptable baud rates that the Arduino IDE will let you set. The smallest is 300 baud, so 300 symbols a second. The highest is 2 megabaud, so 2 million bits per second. Now, generating actual data to send at 2 megabaud, you wouldn't be sending a continuous stream of data at 2 million symbols a second from a 16 megahertz microcontroller. You just can't generate the symbols fast enough. But you could say, if you had them pre-generated, you could send them at a speed equivalent to 2 million samples per second. You just wouldn't send 2 million in a row, probably. Good question. That is so this will kind of transition us into talking about RS485. The reason that the Arduino IDE has a set list of baud rates, right? And you can't just type in. I mean, you can type in. I don't know if it'll compile. Let's see. You type in a random number for a baud rate. I don't think it will compile. Oh, it might. Oh, it did. Hey, isn't that clever? It's interesting that it lets you because you only have one wire to work with. In some sense, when your transmitter starts transmitting, your receiver is trying to receive something, they need to agree on the speed at which they're talking to each other. And having a predefined list of speeds, essentially, means that they will be more likely to be in agreement with each other when they say, all right, is this 300 baud? No. Well, the next base one is 600 baud. It's faster than that. 1200, 2400, 4800, and just keeps stepping up until it finds a speed that matches sort of electrically what it's coming in. Oh no, Palmer had food poisoning. Ugh, that sounds brutal. I'm so sorry. Well, water is good. Electrolytes are good. Our puppy Winnie also had some food adventures this week, so she's hydrating well. So you and Winnie are two of my favorite fuzzy people. So I'm glad to hear you're hopefully on the mend. Speaking of mending things, that's not a great transition. Let's talk about RS485. So we have these challenges with our UART signals, our serial signals, and that noise can couple into them. Their distance is going to be a little bit limited by noise, essentially. Like, noise rejection is an issue when you only have one wire communicating your protocol. So we will use RS485 as one of the ways we can correct that. Here's the little technical details. RS485 is a standard for the electrical characteristics of the drivers and the receivers in some serial style communication, or in one form of serial style communication. Serial in this context isn't the same as Arduino, the serial library. Serial just means one bit coming after another, as opposed to a bunch of bits coming side by side along multiple wires, if that makes sense. This is specifically aimed at low-cost networks when it was developed in the late 70s, early 80s. This I should say, so, and we'll get into this difference a little bit later, RS485 is just an electrical standard. It's not a data standard. It doesn't tell you how to interpret what's coming down the line. It just tells you about voltage levels, it tells you about cable types and termination, but it doesn't tell you how to wrap your data up and send it over a wire, and that'll become important later. Just for reference, in case you want to look up more info on this, and I should say that there are a couple of good links on RS485 in the description of the stream and in the last slide of the slides. You can go and click on TI, Texas Instruments, writes a really good guide on like putting together RS485 networks, which is kind of fascinating, so worth checking out. You will often see it called TIA 485 or EIA 485. The standard basically got adopted by different standards groups over time, and so its name has changed. I think technically the name of the standard is TIA 485/EIA 485 today. They're all accurate. Most people just call it RS485, just so you know. We talked about differential signals a little bit last week, 2 weeks ago, when we looked at making a PCB for DMX signal transmission. I just threw like basically this slide up to say, hey, you know, we weren't focusing on what the RS485 was. I just wanted something to make a PCB out of. But today, that's kind of the gist of the thing. So here's the gist of differential signaling in an RS485 specific environment. You will take 2 wires to communicate any signal instead of 1. We're going to say that when the B wire, so we designate one of them A and one of them B, if the B wire is greater than the A wire by 200 millivolts, we're going to call that a mark value, or a logical 1. And when the A wire is greater than the B wire by 200 millivolts, we're going to call that a space, or a 0 value. Notice that if they're closer than 200 millivolts together, that's in our unallowed region. We're going to say, hey, they shouldn't be that close together. Make sure those lines are at least 200 millivolts apart to say that our signals are going to be accurate. So a signal coming down the line in an RS485 environment might look something like this, where your driver is sending one of the lines sort of higher than the other and then reversing to communicate ones and zeros, and then so on. And then when the system is idling, it might let those lines drop to be, you know, close-ish to each other because it doesn't care what state that they're in. So I will say, this is a little bit of an aside, but if you're looking at RS485 signals on your own, some manufacturers have goofed this up in terms of like which line is A and which line is B. In most development environments, you end up sort of using the same parts for all of your things. So the fact that like a couple of niche developers have kind of gotten A and B backwards doesn't really matter, but sometimes you'll see reference to bit inversion or line inversion. That's what they're talking about. As someone like released their specs saying that, you know, a B higher than A is a space instead of a mark. That's all that is. For our purposes today, you won't need to know much about that, so don't worry about it. It's just a fun nerd tangent because I can and I am a nerd. One of the neat things about the RS485 spec is that it has stronger requirements for the transmitter than the receiver. If you remember way back in week 1, you recall that like a logic level 5, when we digital write something high on an Arduino, we're saying we're going to take it up to around 5 volts, but on the output side, at least 4.2 volts. But on the input side, anything above about 2.6 volts counts as a high. So the transmitter has to do really well. The receiver's route to do, sort of a sloppier measurement, just so we have some slop in our system. So if there was voltage loss over the course of a wire or some parasitics or something was dragging it down, we have some slop on the receiving end that we allow ourselves that we require the transmitters to do better than. So similarly in RS485, on the transmit side, your A and your B line to create a mark in a space have to be at least 1.5 volts different. On the receive side, the difference is only 200 millivolts. For our purposes today, and in a lot of RS485 based systems, the logic levels that we end up using, as opposed to like 0 and 1.5 volts, are what's called TTL level RS485, which means our logic levels are 0 volts, and 5 volts, just like we're used to. Or at least that's what the transmitter is shooting for. So one line will be at 0 volts and one line will be at 5 volts, and then they will invert. And that gives us more than enough of our, our 200 millivolts at the other end of our wires on the receive side. Really quick, so the way that differential signaling helps us out, so all we've done so far is increase the number of wires per signal from 1 to 2. How does that actually help us? So this diagram is a pretty neat way of explaining it. So let's say that in this situation we're sending some kind of an analog signal. like a sound signal, for example, Palmer Jenkins. If this rings a bell to any of you thinking about like balanced sound signals, the idea is exactly the same. Let's say I'm sending this analog sort of hump-shaped signal here. I'm going to send it over a balanced signal line or a differential signal line. What I'm going to do is I'm going to invert that signal, send the inverted signal down one line and the non-inverted signal down in the other line. The inverted signal is marked by this little amplifier with a circle. That's a not symbol. That stands just for inverting the signal around 0. Let's say somewhere on its pair of lines down from the sender to the receiver, some noise gets added into the line. Somebody turns on a carbon arc spotlight right next to the two lines, or someone brings their cell phone too close or something like that. Because the lines are typically very physically close to each other, the voltage difference imposed by the interference will tend to be the same or similar on both lines. So in this case, we say, okay, what happened? Somebody did something that created some electrical noise, and it added this much of signal to both lines here, right? So now the signals are going to look like this, because we had our inverted signal and we added our positive noise blip here, and this, we had our positive signal and it went way more positive with that noise on it. But at the far end, when we subtract one from the other, we subtract this signal from this signal, and we basically invert this and add them back together. What we get is that our signals were inverted to start with, and so they're going to add right back up to our original signal. But our noise, which was additive in the middle here, is not. That's going to sort of flip itself back around and subtract from itself. We're going to be left with just the original signal. That's the gist of differential signaling. If our friend sound designer Dan Carline was here, he would do one of these with balanced signal, right? This is a classic sound designer hand gesture, right? You take a signal that's supposed to be one that's an extant positive signal, you make a copy of it that's inverted, so that any noise that's added to both lines, when you reinvert them, subtracts from itself. Does that sort of make sense? That's kind of a hand-wavy explanation, but hopefully that's cromulent. So that's the gist of differential signaling. In our case, so we don't have the ability to natively generate differential signals on an Arduino. So what we're going to do is make use of some specialized chips or modules or something that generate this RS485 signal for us. There are a lot of common ones. A lot of them work similarly. Some of them are just a little bit different. I put some common part numbers here. The Max 485 is a super duper common chip. The SP485 is like a cheaper version of it. The SN75176 was popular for a long time. You see that in a lot of older lighting equipment and automations equipment as well. And a lot of them basically look like this. And you can kind of see if these kind of remind you of those amplifiers in this diagram with the the amplifier and the inverted amplifier. That's exactly what's going on. They basically are going to take in a signal either at the data in connection on the chip, go through an amplifier that's going to split out a not inverted on the A line here, or an inverted with this circle here to the B line here, right? So send a signal out, or we can set them up to receive a signal, right? They could take in the B signal, invert it, put it into this amplifier, or take in the A signal, not invert it, put those two together, and come out on the RO connection here, the receive output connection. All these chips are basically going to work the same way. We're going to use them in module form. There's a bunch of really cheap TTL level RS485 modules you can get online now. I put a link to a couple of them in the description. But basically the circuit we're going to wire up is this. Our transmitter Arduino and our receiver Arduino are going to do basically the same thing. We're going to use our two little modules that I'll show you on the bench in a sec. We're going to hook our TX line of our Arduino, just that digital pin 1, to the TX line of one of our RS485 modules. We're going to string A, B, and common wires between the two of them, and then RX on the receiver module to RX of the Arduino. So let's do that. Come over here and take just a second to wire it up. I'm going to unplug both of them as I usually do. In fact, I'm going to pause for a second, mute myself, and take a drink of beer, because I think I've... Oh, zombie dust. Tastes like zombies. All right, so what I have are these little tiny modules. That is the Max 485 chip right there. These, if I were to buy modules to play around with today, I actually wouldn't buy these. I think I put a link to them in the description still, but there's a style that has terminal blocks on the end that just makes it a lot easier to deal with. I would prefer to get those. But you can see, so I basically have the RS485 chip and some supporting components that we don't actually, strictly speaking, need. This one has a buffer, so you're left likely to damage something if you didn't know what you were doing. It also has these big fuses that are meant to trip, so you could it claims that you can like have lightning protection in your system by using these. If I was worried about lightning, I wouldn't use a little module that cost me $6.99 for 2. I'd probably go a little bit more robust. But that's what all this other componentry is. It's not strictly necessary. It's just kind of a function of this module. It's also got 2 little LEDs that are connected to the TX and RX lines that'll flash when they're transmitting or receiving. So that'll give us a little visual indication of some of the things that are going on. Let's go ahead and get these wired up. So on the TX side, take my TX line back here. I've already got a few things pre-wired up here. I've got my power and ground wires hooked up to the power and ground rails of my breadboard here. I'm going to plug in this transmitter side thing here. So it's got power on the VCC pin, where VCC just means power. You've got a ground pin there, so ground is hooked to ground on the Arduino. I'm going to hook my TX line up to the TX pin there from the TX position on my Arduino. There's that. Right? And that's all the TX pin, the TX side setup is. On the RX side, the receive side, very similar. Going to do power, ground, and then the RX pin on this guy. Why don't you focus? There we go. Power, ground, and then RXD will connect to the RX pin on the Arduino. And once again, I kind of already have it set up. So I've got power and ground connected from my Arduino to the power and ground lines of the breadboard, power and ground, and then I'm going to hook up this to the RX side of things, right? So now all that remains is to actually connect the 2 modules. So I'm going to use, just so we can play around with them, some of these guys, which are alligator clip leads, which are one of my favorite tools to keep on the workbench when I'm monkeying around with stuff like this. Second only to, like, DuPont wires and things. Because really easy to, I want to throw a connection on there, or I want to break a connection. So I've got 3 connections to make. I'm going to connect my 2 commons together. Common on these boards, actually, it's A plus, B minus, and the common has a symbol in Chinese that I can't read, but I assume means common. I don't know what that means. But that's all right. I don't really have to. So, connect my B connection with my white wire. If I'm being very good, I'll follow the same color coding that's in the diagrams and the slides, because I got a little fancy with it. I really enjoy making the slides for these weeks. I don't know if I've shared. I often start the process being like, I don't know how I'm going to turn any of this into slides. And then by the end of the week, it's like 40 slides later, and I'm having a great time. All right, those connections are made. The 2 things are hooked together. And I remember, so I haven't re-uploaded any code to these 2 Arduinos. So we're going to take our TX signal. Remember, our demo is still running. This is generating a value dimming from 0 to 255, setting this LED to match. When this receives a value between 0 and 255, it will dim this side to match. All I've done is basically taken the UART signal, fed it into this RS485 transceiver, and with a little luck, and we'll see if we have it tonight, it'll basically send that signal out over RS485 as a balanced signal over to this side, where it will get decoded back into a single wire signal, and into this Arduino. So let's plug the receive side in first. We'll see its little heartbeat light is going there, so it's alive. And I plug. This is why I have the heartbeat, right? So we know this one is doing its thing, even though, of course, it's not, it's receiving any signals lit, so it's not dimming anything. I'll plug the transmit side in, and when that starts running, yeah, there we go. So, ooh, a little loud there. Sorry, I got a little excited. What happens if you do A to B and B to A? Good question, Chris. 2 answers. One is, so the electrical answer is right, is that a 1 would become a 0 and a 0 would become a 1, because whenever the data should be, a 0 when A is below B, now B will be below A, and vice versa. So implementationally, what that means is most of the time nothing will respond. So actually, I will do this on the receive side here. I'm going to just reverse my connections. And I sort of doubt it will do anything. Yeah, I actually have nothing happening here. I was shorting something out to my control board. Yeah, so nothing is responding. I thought I smelled burning there for a second, which is kind of exciting, but but in theory, nothing should happen. I think there's just a general smell of burning in the air this week. Here we go. hook those back up right. So with 0 being with 0 and 1 being inverted, typically that will leave your data in a state that your system doesn't know how to interpret it, and so it will just stop. Right, so in this case, if you took what is a UART signal and made all the 1s 0s and all the 0s 1s, there's enough structure in that communication that it's going to say, hey, I actually don't even know where to start with this. I'm just going to assume that something has gone wrong, and I'm going to stop. That's most of the time what will happen. It's not actually the job of RS485 to make sure that happens. It's the job of the higher level protocol that you build on top of it, but we'll talk about that in a second. So I guess before we move on, that's a really simple, straightforward, easy way to use RS485. We have like a working, useful demo, and we're a real, not even a Jeff Glass 40 minutes in, we're a real 40 minutes in. So possible applications of this. Here, I'll talk about possible applications while I set up the next little mini demo. I'm just going to unplug the transmit side. If you are working with any kind of sensor, a remote actuator, or something like that, I keep going back to the example of, I've got a temperature and humidity sensor, say, on the outside of my house, and I want it to display inside my house. Whatever protocol that temperature and humidity sensor speaks, whether it's just returning an analog value, whether it's doing something like UART or maybe SPI, which are other sort of one-wire signals, is probably not going to be super reliable over more than a handful of feet, maybe a dozen feet or so. So one thing you could do is put an Arduino at the sensor, say, on the outside of your house, have it send that data via the UART into an RS485 transceiver, have it sent through a pair of wires, I guess 3 wires, right? So a pair of wires and a common ground, to another Arduino that's going to decode it and then do your display. That would be a really easy way to use something like this. Just to demo that a little bit, I'm going to plug in a little potentiometer here to the transmit side and load up another demo. This is the, what did I call this? The send knob demo. Let's see, what did I call this demo? Stream. This is the knob send demo, so if you're playing along at home. A very, very similar demo. It's this time, instead of sending a value that's constantly incrementing, I'm going to be sending a value that I get from an analog read of a pin that's fed by the potentiometer. So I'm defining my potentiometer as hooked up to pin A0, going to make sure in my setup function that it's an input, and then down in my loop, here's where instead of doing that value equals value plus 10, I'm going to say value is take the analog read of that pin, and then map it, since analog read gives you a value between 0 and 1024, and I only want a value between 0 and 255, use that map function to sort of scale that value down. And then again, just push that out over the serial port. So let us plug the transmitter back in, and we will upload that code. Upload. Boop. Papu is not declared. That's no good. Oh, did I capitalize it differently? Probably. Yeah. Yeah, Nate's got it. Nate's got it. And this is why I can't do these things on my own. So now instead of constantly incrementing, I have my value sort of constant here. Hopefully, as I rotate the potentiometer, I still have a delay in here. It feels like I do. Yeah, So I actually don't need this delay in here was to prevent me from incrementing that value too fast. I'm just going to take that delay out of there. Just give a little bit of a smoother dimming. We'll upload that. And we come back over here as I rotate the potentiometer. Yeah, there we go. So now we're really starting to see the so this LED is directly, and I've got a little bit of jitter because I've got like a loose connection here somewhere. But you can see as I turn this one off, there's a little bit of delay, right? Because it's taking a little bit of time to send that signal out. The transmission across the wires is nearly instantaneous. It takes a little bit of time to receive it on this end, right? Maybe a third of a second of lag there, just based on the serial communication that's happening between the two. I think that's what our delay is from. Let's see. I didn't plan on this, so I actually don't know what'll happen, but I suspect if I bump up the serial rate to one of the higher ones, say 115/200, I think this will help our lag somewhat. And this kind of brings me to a useful point if you're experimenting with this on your own. If I were to try and upload something to the receive Arduino right now, let me show you what will happen. Because I'm going to need to change the serial rate over here. So I'll select COM port 3 and try and upload. And you'll see I get stuck. Now I have the verbose programming mode on here, but often you'll see like I'm trying to program the Arduino and it will just pause right here. It'll say uploading. It's spinning its wheels in my window, blue window of death. have my full progress bar here. What's happening is it's trying to upload, but of course it's trying to upload using the TX and RX lines of the serial port, but I'm slamming the RX line with this incoming signal from my RS485 transmitter. So to get this thing programmed, I'm actually going to have to disconnect my RX line, and then typically I'm going to have to re-upload to make sure things take. So many systems that upload are smart enough to say, hey, now I can see that, I'm going to retry sending it. What I find is the more reliable method. You see a problem uploading to board, couldn't do it. Now when I set my serial rate, because I'm no longer clobbering that RX pin with unrelated data, I should be able to upload just fine. Then I can come back to the table, I can plug my RX pin back in. And now as I rotate these two things together, yeah, that lag is radically decreased. I can't see any with my own human eyes here. I don't know if you can on camera, but I think that's pretty much eliminated that. So that's just like showing you that there is some overhead in the timing of sending a serial signal, you know, between one device and another, queuing it up, sending it out, receiving it, especially at 9600 baud, it's just not happening particularly fast. At a much faster baud rate, you get much less delay. So, interesting thing happened there. We'll learn something together. Questions, comments, issues, concerns that take a slip of zombie dust from Three Floyds Brewing Company here in the Midwest? Oh, as always, feel free to jump in with questions while I ramble on about nerdy things. Happy to try more stuff. Let's take a look at a few more thoughts about RS485, though, as people are generating those. Oh, Palmer, how much overlap is there with RS232? Good question. So RS232 basically is TTL levels, is UART serial. So they share some characteristics, but they're not exactly equivalent. Here, let me show you. You're over here now. So RS232, I want you to, if there's a signal diagram. So RS485 is just a differential signaling protocol between two lines. RS232, yeah, here we go, represents data levels on a single line above or below a common ground between the two devices. So when you're using a UART on the Arduino, you are very literally using RS232. It's running at those serial levels. Yeah, so here we go. So asserted is +3 to +15, and mark as deasserted -. Actually, I don't. This is not our. This is yes, this is the thing. So nominally, RS232 is positive and negative voltage. A lot of the standard has gotten sort of borrowed into UART serial. So I guess technically on paper, the Arduino UART is not RS232, but it shares a lot of its characteristics with. There is a term for that, like bastardized RS232, if that's not what it is, but I don't know what the term is off the top of my head. So not a ton of overlap, though they are both methods of like getting a signal from one place to another, if that sort of makes sense. Fair question. I will fully admit I don't know the full answer. Let's see, where were we? Oh, okay. We talked a little bit earlier about how speed of communication and distance are sort of a trade-off, right? For RS485, here's what that trade-off looks like. So nominally, you can get up to about 1,200 meters out of an RS485 line if your speed is slow enough, or you can get up to about 10 megabits per second onto that line if your speed is if your distance is short enough. The rule of thumb that gets tossed around, and this is a little bit questionable, but like your data rate in bits per second times your distance in meters should be less than 10 to the 8th, is like the thing that you can sort of like roughly math out. So that works out to, a kilometer at 100 kilobits a second, or 10 megabits a second over 10 meters, right? So again, the longer your line is, the more work essentially your transmitter has to do to drive that line up and down constantly. So the slower you go, the longer that line has to stabilize in a state closer to a positive differential voltage or a negative differential voltage before the receiver has to read it. These are some rough measurements. Here's a little casual graph I stole from somewhere, showing like, for a very short distance, you can get a really high speed, and for a very long distance, you can, as long as you run a low speed, you can get up to a kilometer away. This is one of those things that makes this a pretty common physical protocol to use in things like factory automation, where you're not sure, if my sensor and my digital my PLC, my digital computer are going to be, maybe they're next to each other, maybe they're, several hundred feet away down in a control room. As long as you have this sort of ability to be flexible about your data rate, RS485 can do both, if that makes sense. So here's a little one further way of thinking about it. When you're thinking about how fast your transmitter is going to slam the difference between those two lines apart, essentially, right? It's going to have to work to constantly invert and uninvert those lines. One thing you might choose to do is run your transmitter a little slower on purpose, if you will. That's called adjusting the slew rate of the transmitter. And you see these two pictures down here. This one over here on the right is what's called slew rate limited. It's just kind of a gentle curve from up to down, It's only going to, at a slightly slower rate, try and hit those peaks and troughs of that signal. Obviously, this is only measuring one of the two lines. It's sort of more measuring the voltage difference between them, more like. Whereas this one over here, our non-slew rate limited transmitter, is really just going to set these things to a positive voltage and a negative voltage as fast as it possibly can. This has implications for RF interference. The faster you change an electrical voltage, the more electromagnetic interference you're going to create with that wire. Because these very sharp, abrupt changes in electrical voltage level represent a high frequency rate. How do I explain this? Have a lot of high frequency components in them. Whereas these, which have softer curves, basically are closer to a sine wave, if you want to think of it that way, are closer to a single frequency signal. And so if you look at their graphs down here of intensity versus frequency, you can see this non-slew rate limited signal has a lot of harmonics at various power levels going up the line, whereas this slew rate limited one, those harmonics fall off much more quickly. Now, of course, with this slew rate limited signal, you're limited to a somewhat slower speed. But your trade-off is you produce less electromagnetic interference, and if you have, dozens or hundreds of these lines in your industrial automation environment, maybe that's a desirable thing, right? The whole point of this was to avoid noise in this own signal line. It'd be great to kind of help, prevent noise from leaking into other adjacent lines. So when you see parts like, the MAX 485, sort of a canonical example of one of these chips that's a RS485 transmitter, you'll often see right next to it the MAX, say, 487, which is the exact same thing, but slew rate limited. So it's going to have a slightly slower data speed for the trade-off of less electrical interference. For our purposes, over distances like we're talking about with a few feet, it really doesn't matter. It really only comes up in industrial automation environments where you have dozens or hundreds of these things put next to each other. In general operation, it doesn't typically matter. You can choose to use a slew rate limited product or not, if that sort of makes sense. Another tangent that's not directly relevant to you, the maker at home on your workbench, but I think is nerdy and fun and cool. Little tangent over here. A tangent within a tangent. I'm so sorry. We'll carry on soon. This is straight from that TI design guide that's linked in the last slide of this thing, and I think in the description of the stream. The maximum stub length. Let's put a pin in maximum stub length. What I want you to notice for now is the slower the signal rate, the longer the maximum stub length. What is maximum stub length? Well, we'll get to it in a second here. When we talk about topology. So RS485 has what's called a linear bus topology. It's meant to have things connected, one connected to the next, connected to the next, connected to the next. So you have this line essentially of things all connected to each other with very short, possibly bits of wire branching off that main one and going into the main computer. So in a lot of devices, what this looks like is, if you're familiar with lighting devices or things, that would run off of RS485, you often see them daisy chained together. So you plug a cable in, and you plug a cable out, and you connect one device to the next, to the next, to the next. Inside the device, right, what's typically happening is those two connectors are connected directly to each other by a very short bit of wire, and then there's, a few inches of wire going into a circuit board somewhere. So technically, right, you don't have that device connected perfectly through itself. You have the device connected in, you have a little stub of wire coming off, and the rest of the wire continues on. For our purposes, that's fine. And that's what stub length refers to, is like, how long can that diversion from a truly straight, just one piece of copper running down your factory floor, how long can that be? And then again, it varies by signal rate, but for the kind of rates we're talking about, as long as it's less than a few feet, you're probably fine. In RS485, things are designed to be laid out in this kind of linear fashion, one connected to the next, connected to the next, connected to the next. They are not going to be in a star configuration, right, where you might have a bunch of RS485 lines coming together and then branching out in all directions. So no T-splitters in RS485, no octopuses, nothing like that. You could have something like a tree configuration where you have active devices in each side, where you have basically a powered splitter that takes in a signal and generates its own little RS485 sort of separate connected network on the other side. That's fine. What you then have is basically multiple little RS485 branches all over the place, but you don't want just a bunch of, like, you wouldn't take like 5 wires and wire nut them together and then star back out from there. That makes sense. We're going to focus on linear topologies. At the connection level, going back to this little symbolic representation of what's going on inside of our chips, we have a transmitter and a receiver with an inverted side and a not inverted side. There are a couple of different ways you could lay this out, because of course it takes 2 wires to do a single direction of communication. Much like on our board here, we had our TX line and we used up, so to speak, these 2 signal wires getting the signal from here to here. If we wanted to send a signal from here to here at the same time, we would need another pair of wires. We could have a situation where we transmit something from the transmit side to the receive side, then the transmitter turns itself off. This, Arduino knows it's time to transmit something, turns its transmitter on, and reuses that same pair of wires to send a signal back. But each pair of wires can only send a signal in one direction at the same time. That's what's called a half duplex or a simplex mode of communication. Basically, simplex meaning it can only flow in a single direction at a single moment. A lot of these systems, where we're talking about lighting control or factory automation, are set up so that there is a single sort of main controller, master controller. Maybe it's your main computer that's controlling all of the sensors and servos in a robot, or maybe it's your lighting control console. So often in these diagrams, you'll see something like, a red, like a master communicator, and a bunch of other subservient communicators. And the master, in a situation where it did need to receive information back, would be sending information down both of these lines, and then would say, okay, now this device, I'm going to turn my transmitter off. I want you to send me back this very specific piece of information, which it would then do. And once it had done, it would know to turn its own transmitter off, and the master would say, thank you, I'm going to be carrying on with my programming now. There's not a reason why you couldn't have multiple devices negotiating sort of who was going to talk when, but in most practical applications, what you end up with is a single master device sort of telling the other devices when and if to talk, if that makes sense. From the wiring standpoint, you should look at it like on a chip level. Again, so we have our couple of chips with our transmit and receiver in them. They're sharing the same pair of wires, and it's just up to our programming to choose when is one side transmitting and the other side receiving, and so on. You can set these up so that you have what's called full duplex communication, but you need 2 pairs of wires, right? So you have a set of signals constantly coming out from your master communicator, a set of wires that are constantly carrying signals back. Now, of course, all of these other subsidiary devices would have to negotiate when they were allowed to take control of those signal lines, essentially, and send signals back. But you would need sort of 4 wires to do this. This is what's called full duplex communication. And depending on your environment, this is not terribly common, but it can be done. It electrically looks just double like what we have set up on the table here today. This is what it would look like sort of electrically at a circuiting level. You would have a chip that was designed to communicate on 4 wires at once. So a pair as transmit and a pair as receive, hooked up the other way on the other side. This is the Max 3467. There's lots of different chips from Maxim and other suppliers that'll do essentially this thing. I need a sip of beer because that was a lot of words. Questions? What I need like a big fat, like one of those easy buttons from Staples that I just hit and it mutes, or it just says beer and I mute it. That seems like a thing we could build with Arduino. That seems plausible. There's so much, in this age of streaming, there's so much like streaming related stuff that we could build with Arduino-y things, like because the Arduino can serve as a serial communicator, and OBS and a lot of streaming softwares will take a connection either from a serial port directly or through like a Python program or something. That would be kind of a fun. You can do a lot, basically, is what I'm saying. That's like a tangent within a tangent. Nate says foot pedal mute? Yeah, that would be cool. I used to have a foot pedal. for something that I bought at like a swap meet for $2. I think I tossed it in the last move, and that was probably a good idea, but now I wish I had it. Carrying on, we'll talk briefly about termination because I want to get to some more demos, and we have lots more stuff to talk about. And it's been an hour. Termination. So termination refers to basically putting our resistor at either end of your signal line to absorb the signals so they just don't bounce back and forth forever. Chris says, having full duplex with 2 wires and more than 2 devices is super complicated because of knowing who is transmitting, right? I wouldn't say super complicated. I mean, in the full duplex... Oh, full duplex with 2 wires and more than 2 devices. So Chris, that situation where you have... Here, let me scroll back. So, like, I think what you're saying is in this situation, right, where we have a pair of wires, we have multiple devices in the network, and they all sort of want to talk to each other. Yeah, you would need to have a protocol built in to your system that basically has some methodology for agreeing who's going to speak when, right? Like, we can't just all shout over each other. We have to sort of delegate or communicate our signal control. And that's why a lot of the times you see set up with a system where your main controller is responsible for sending, its messages might be like, block 1, sensor 1, send me your value at memory address 1234, and then it will shut up. Typically for like a set amount of time, it'll shut up for 2 seconds and listen for the response from sensor 1. And if it doesn't get it, it'll say, okay, well, sensor 1, you missed your chance, I'm carrying on. And in those 2 seconds, sensor 1 will take control of those lines, send its signal, and then shut its transmitter down. And then the master will pick back up and say, okay, now sensor 2, send me your value, read me your sensor in this position, give me this value in memory. Or, hey, sensor 2, or, hey, servo motor 3, I want you to move to address 130 and tell me when you're done. Things like that. Travis asked about RDM. So I want to put a pin in RDM, or remote device management, because yes, that is ish how it works, but RDM actually does some really cool things in terms of figuring out who gets to talk when. So let me put a pin in that until we've talked about DMX, because it's actually really cool. Essentially, Travis, yes, each device has its own unique ID, but it's a little bit cleverer than that. But for those who may not have run across like the finer points of DMX, I want to talk about that real quick first, real quick, and then I want to talk about RDM. I don't have slides for RDM because I wasn't necessarily planning to talk about it, but it's really cool, so we should. All right, where were we? Termination. Oh, so real quick, so the reason for termination is that if you have, and I'll just gesture at some wires in physical space here, because it's gonna be a little bit of a hand-wavy explanation. If you have some signals moving down a wire and they get to a point where the wire stops, or alternatively where there's a really high impedance connection, right? So this receiver is trying not to bog down, load down these lines at all. It's acting just like, open space. When the electrical signals from this transmitter get to this receiver, they will naturally sort of hit the end and bounce off and come back down the line over to the transmitter. And that's typically not something we want, especially if your line is long enough. By the time you get to the end and signals bounce off and they come back toward the beginning, now we have voltages sort of moving one way and voltages moving the other way, if you will. And if your distance is long enough that those start to get separated from each other, you can start to see, one bit overlapping with the next bit, and they just sort of start to appear as noise, and your signal gets very confused. What we'd really like is for this signal to be transmitted by the transmitter, get to our receiver, and then be absorbed by something, turned into heat by something like a resistor. So we put termination resistors at either end of our signal to basically absorb the excess electrical energy and stop it from bouncing back and forth inside this electrical wire forever. In RS485, the termination resistance is 120 ohms. So for those of you who've used a DMX terminator before, you're basically putting a 120 ohm resistor across your 2 signal lines, and that just prevents that signal from bouncing back and being absorbed as a signal at any of your subsidiary points along your RS485 line. One thing that's in the RS485 spec that's kind of neat, again, just tangent, is if you have a really high noise environment, you can do 2 60 ohm loads in series with a 220 picofarad capacitor to ground between them. Capacitors tend to pass high-frequency signals and block lower-frequency ones, so this will tend to, allow, but while providing termination, will allow high-frequency signals to shunt to ground. I'd never seen this before I started digging into the spec. It's kind of an interesting thing. It basically forms a low-pass filter on your line at a pretty high frequency, like a couple megahertz, but certainly higher than the frequencies we're interested in. So anyway, a little nerd tangent there. You will also see terminations like this, where you have 120 ohms across the line and a resistor to a positive voltage, like in our case 5 volts, and a resistor to ground, to a negative voltage. And this is to ensure that if no one is transmitting on the line, right, if we all have our transmitters turned off, that the signal lines are in a defined state. So basically a pull-up resistor and a pull-down resistor on each of our 2 signal lines, right? So if we've sort of stopped transmitting on something, these lines will naturally tend to flow toward a state. I think it's supposed to be a mark state by the spec, right? To actually tend to form toward a logical 1. And that's just good so that you didn't have 2 lines sort of floating in reference to each other that might, in some configurations of noise voltage look like data that could be interpreted by something. So you often see, especially in industrial equipment, this sort of termination where there's a pull-up resistor on one line and a pull-down resistor on the other. And that just gives you a defined state if nothing is happening. And speaking of things existing in a defined state, just to get a little into the weeds on this, because if you weren't nerds, you wouldn't be here. So I don't feel too bad about getting kind of nerdy, because I feel like this is the place, right? I don't know if you can hear my dog in the background. It must be fireworks o'clock. I apologize. She's really cute. I don't know if we'll get her on here ever. She's not allowed in the workshop, but sorry for the barking. She's really cute. Talking about maximum number of things on a single RS485 wire, RS485 has this concept in the spec called a unit load, which essentially is like putting a 12K resistor to ground or between the 2 signal lines. A very small amount of load. That is what's called 1 unit load, one small bit of like drain on your signal lines. And the spec says that every transmitter must be able to drive at least 32 unit loads. This is why if you've seen on a DMX spec like, hey, don't connect more than 32 devices in a row, this is where it comes from. Now, the thing is, in modern times, right, so, when the spec was developed in the late 80s, having a receiver that was acting like a 12K resistor to ground was a pretty reasonable thing to expect. Nowadays, receivers are really good. They don't put much load on the lines at all. So some receivers, you'll see like, hey, this presents a half unit load or a quarter unit load. Some as low as 1/16th unit load to the lines. So if you have a bunch of devices that all present a 16th of a unit load to your line, you could put up to 256 of them on a single RS485 network, no problem. But for safety, assuming that there's older gear out there in industrial and lighting and all these other applications, you always just sort of assume that any device could have a full unit load of drain on your signal lines. And so a lot of the times, when you're looking at an application spec, it'll say no more than 32 devices connected in a chain. That's where this comes from. I should also say this biasing, when it exists, this also, of course, puts some pull on your signal lines of about 20 unit loads. So you take that into account when you're designing your system. Anyway, being a nerd. But yeah, so this, when you see like this receiver has, presents a quarter unit load to your signal lines. This is the math that they're asking you to take into account. Chris says, when I wrote this question down a while ago, taking the ETC DMX class, how are we able to put more devices on a DMX line? Because they take smaller loads? Yeah, exactly. So a lot of modern DMX devices will be incorporating receiver chips that are putting far less than a single unit load on a line. They're presenting a very high impedance to the signal line. They're really not draining it at all. And so, you can start looking at, dozens to a couple hundred, units on a line before you really start to see issues. A lot of, like commercial lighting projects, for example, like DMX nodes will still say no more than 32 devices connected in a line, but that is not necessarily a hard and fast rule. That's just sort of manufacturers like covering their butts and saying like, assuming everyone did like the minimum required thing, if we just tell people they should assume that everything's putting its maximum allowable load on the line, if we just tell people don't do more than 32, they'll be safe and they can't call our tech support and yell at us. That sort of makes sense. I wonder if this is an experiment again, just to like do things live. I wonder if we look up the Max 485 datasheet, if it will tell us how many unit loads it presents. I think it should. Let's just search for. Here we go. Unit load. So is this the right datasheet? Yeah. So fault tolerant quarter unit load on the Max 3438. Let's see here. unit load, units. I want unit load. There we go. Quarter unit load. Yeah, so it looks like these are maybe a half unit load, but if you wanted specifically a quarter unit load device, you get this Max 487 chip, 128 transceivers on the bus, on the control bus it's advertising, right? So, yeah, so here it's spelling it out. If you want a quarter unit load receiver, use the Max 487, right? You can put 128 of them on a standard RS485 network. What happens when you exceed the limit? Devices kind of freak out or don't work. It really depends on the device and depends on your specific network topology, right? So every time you continue to load those lines, right, you're going to start basically affecting the transmitter's ability to separate them in voltage as it switches between those mark and space states. And so what happens is going to be dependent on cable length, is going to be dependent on signal speed. As at some point, the lines are not going to necessarily be able to settle into a mark or space state before the receiver is expecting sort of the next bit of information to come in. And so what it reads is going to be a little bit indeterminate, right? You can imagine a situation where your lines are so loaded that, we had a mark state where you have a logical 1, and then the lines are trying to transition, and then the receiver's like, okay, I'm going to read my voltage here, and whether the RS485 transceiver says this is a 1 or a 0, if they're within that 200 millivolts of each other, who knows? So you start kind of getting gobbledygook. How gobbledygook depends on your system implementation, and does that translate into actual data? I would wager probably most of the time not. But if you want to think about like what happens when you don't terminate a DMX line, right? When you start seeing sort of ambiguous values at your receivers, very same thing could happen if you started overloading that line as well. Chris says, good questions all. Does opto isolators mean that each split line can have 32 devices? Yes. An opto isolator in lighting terms, and I should clarify because opto ISO means a little bit more than what we typically use it as. Opto ISO DMX means we're thinking of something like, let's see. Yeah, like one of these guys, like a Lightronics IDP 104, of course. No, these are ancient, but and I swear, for those who haven't encountered DMX, it's a protocol built on RS485 that we're going to talk about a bunch this evening, but you have DMX, you have a signal coming in at one place and being replicated in 4 places. This is what we in the lighting world would call an opto ISO. Opto ISO in the electronics world just means a method of using light, like optics, to separate 2 signals electrically. In the lighting world, we typically mean a thing that splits DMX and has this optical isolation built in. And to Chris's question, yes. So you basically, inside an opto ISO like this, you have an RS485 receiver chip. You have typically a buffer, just for good measure. Maybe you have a level of optical isolation, and you have 1, 2, 3, 4, in this case, transmitters. So what you essentially have, instead of one long RS485 network, you have an RS485 network that consists of just this segment and 4 separate networks, each of which could have 32 loads on it on the output side. So yes, so you could have up to 32 unit loads on each of those 5 different networks, I suppose, at some point. How much like processing these optos do is sort of up to the opto itself. But yes, and this kind of thing exists for various protocols built on top of RS485 as well. Where do we go next? Oh, we go to a demo. Good, I was hoping there'd be a demo soon. So this is the circuit I'm going to build up now. You'll see it looks a lot like our previous circuit. I got a transmitter Arduino over here. I have my 2 different Arduino receivers over here. You see my wires go from my transmitter to my first receiver and then over to my second receiver. So I'm not going to kind of star them all together. I'm going to try and be good as much as I can, get one to receive, the wires go straight to one and then sort of branch off close to that one and go to the other. So it'll take me just a second to build that circuit up. If you have questions or beer thoughts or weather updates in the meantime. So let's see. I'm going to need another Arduino. So I'll zoom out a little bit here because I'm going to get even more desk space covered. There we go. So bring the other Arduino in here. Let's see. I need some more wires. So I've got some more of these alligator clip wires here. And I think I've got my color coding all sorted out. So actually, before I wire this up, you can see I'm not using one of my RS485 modules here. I'm using just a raw 75176 chip here, which is the same pinout as the Max 485, the SP485, all the same. Basically, someone made a pinout for this chip, sort of connections and the order that the connections are in on the chip, and everyone else since has sort of matched it, more or less, just so they could be interchangeable with each other, which is both smart and good business sense. So what I'm going to do, I've pre-color-coded my wires here to help me out, is I'm going to clip my green onto green, and I'm going to clip my green onto this fake green wire here. That's going to be my common, or my ground. A little tangent, because we haven't had enough of those tonight, while I'm setting this up. There are, in the RS485 spec and in that TI design guide that's linked, some good reasons actually for not using your ground connection as your signal common connection. You can end up with what's called ground loops if you have a long enough distance between your two objects, where basically current flows along your ground wire because ground in one place might not be ground in the other place. And there are some strategies, including isolation and ground resistors and things that can help sort of alleviate that. For our purposes, I'm just going to say ground is common is ground. It's not ideal practice in an industrial application, but like I said, that's a tangent that's beyond the scope of tonight, but worth mentioning. So let's see, what am I going to do to demo this here? Well, I guess I should upload some code onto this Arduino first. So this will be my receive Arduino here. Let's get some code on there. Let's upload that same basic receive code onto that. We'll get that uploading. Make sure that works. Oh, yeah. Once again, I need to disconnect my receive line here. Let's do that on the Arduino side. So unplug that. And typically, let's see. I'm just going to plug and unplug the Arduino. This helps it get unconfused. Now when I come back to upload, hopefully we'll upload successfully. Reading, writing, done. Great. All right, so now that is connected. So I'm going to plug my receive line back in. I'm going to plug my transmit line back in. And now we should see, so this Arduino and this transmit Arduino are running the same code they were before, so I now have control over, let's get them all on the screen there, and I have control over both of them using this potentiometer hiding down at the bottom of the screen there. And then if I plug this Arduino back into power, I got a sketchy connection over here of some kind. You can see that I now have control of all three of them. The signal is coming out of this Arduino, it's coming into this 485 chip, and it's branching onto this 485 chip. And the same signal is going into both Arduinos, and so they should be responding in the same way. Assuming I don't have wiring issues, which kind of, something is, oh, my connection down here is very sketchy. There we go. So now you can see they're all sort of dimming in unison. Travis says, remind me to tell you my story about when we fried 20 different RS485 chips and various moving lights. I do want to hear that story. Oh no. That's often why, especially in older equipment, you see, oh, something is, I've got a loose pod connection here, I think. There we go. It's often why in a lot of older lighting equipment, especially, you see the RS485 chip even if the board is like new and modern and like surface mount, you see these chips in removable sockets on the board, specifically because if you put too much voltage into them, you can fry them, and they're meant to be an end user serviceable part where it's like, oh, somebody put 120 volts on my signal line, this chip popped, everything else is fine, pop the chip out, plug it back in. But I have a bunch of these little 75176 chips left over from repairing Express boards back in the day, Express lighting consoles for those who know them. Travis says, Apprentice C-clamped straight into a Morpheus scroller cable. Ooh, sending 48 volts into RS485. Ah, that's too many volts. I wonder how many volts a Max 485, for example, can take. Let's see. Let's do a little data sheet dive, because we haven't done enough of that tonight. And then we'll move along to our next example, I swear. We're doing okay on time for what I reasonably expected would happen. Oh, here's a thing in the beginning of the Max 485 datasheet, Chris. Number of receivers on bus. So this is telling you like the Max 485 is a full unit load, but the 487 and the 1487 are quarter unit loads. Interesting. Absolute maximum ratings on the driver input voltage, on the receiver input voltage, -8 to plus 12.5 volts. So 48 volts would be a smoky, sad time. Woof. Travis says there's a spare RS485 pins in the color and power supplies for. Yeah, exactly. Like, this is the kind of thing that just happens when you're in a rough and tumble application environment. They just expect you to be able to replace these things, and so they make it possible too. So one thing I want to point out about this demo, right, is I have a single Arduino sending data, and both of these Arduinos are getting identical data, and they're therefore acting on it identically. And modulo my sketchy wiring, right, which is something a little freaking out. I don't really have a way at this point of making these Arduinos do separate things. Even if they are running separate code, they're getting identical commands, identical data out of this Arduino. So we're in many ways, we're just sort of stuck with them doing identical things. We would need another sort of layer of communication built on top of these to start making them do separate things, communicating with them separately. And that is my segue into the OSI model. All right, I'm sipping the beer before I start because this is kind of a dive. But bear with me, nerds. This is cool. I had considered at one point going to like a Manhattan for tonight, and beer was 100% the right choice, so no regrets. The OSI model. It's a little bit tangential to what we're talking about tonight, but what is it? OSI stands for Open Systems Interconnection. You don't need to know that, but most people don't, so now you do. You can one-up your nerd friends. The OSI model, it just really came about from people digesting what networking, like Ethernet-style, Internet-style networking was, trying to break down how a communication stack works into a series of layers where each layer is sort of built on top of the layer below it and can be swapped out for another version of that layer without the layers above or below necessarily knowing anything. It's a way of layering processes on top of each other in sort of an interchangeable way. And if that doesn't make sense yet, it will by the time we get done talking about this. So the OSI model has 7 layers, but there's really only 5 that matter. So we have the physical, so these layers go from lowest to highest. At the base, we have the physical layer, and we're going to talk about each of these in turn. Physical layer, data link layer, network, transport, session, presentation, application. That's our 7 layers. The lower layers are what are typically sort of our purview as electrical nerds or electrical engineers or systems engineers or things like that. Everything above the transport layer tends to be built in software and starts to get a little bit mushy. The session layer is really built on, usually built into the transport layer. Presentation is often built into the application layer. So really, in a lot of applications, what you have is physical, data link, network, transport, application, right? 1, 2, 3, 4, 7. These two are kind of thought up by academics back in the day and don't really exist anymore. But just so you know what the 7-layer burrito looks like, that's what it is. So at the bottom, we have our physical layer, and this is where RS485 lives. And that's why we're talking about this OSI models. I want to show you where RS485 fits into our understanding of networking, so we can understand how to build on top of it. So the physical layer is responsible for defining the unstructured medium of communication between 2 directly connected devices. So that's things like voltage levels on your wire. Going back a step, physical medium. Is it voltage levels on a wire? Is it light levels for an optical, like a fiber optic communication? Is it RF levels in the air? Is it audio tones for like an old DSL style modem? We're talking about physical differences. What makes a 1, what makes a 0 in our environment? So we know for RS485, a mark, a 1 is 200 millivolts greater on one end, a space is 200 millivolts greater on the other. That's a physical layer definition. Additionally, things like, our line impedance, the fact that we're using 120 ohms as our termination resistor is a part of the physical layer spec. The fact that the wire should be, close and bonded, the fact that we're talking about copper wire is all part of this RS485 physical layer spec. It'll define maximum distances. It'll define signal timing. It doesn't have anything to do with what the data itself is. The physical layer just defines, what is a 1 and what is a 0 in this medium. So some examples, RS485, of course. RJ45 or 8P8C, the physical connectors that make up like an Ethernet cable, right? The spec is an 8P8C connector has a physical layer component to it. You often will also hear about like 10 base T, 100 base T, 1000 base T. If you go back a ways to 10 base 2 Ethernet, things like that. The 10, 100, 1000 base T parts are the physical spec defining how the ones and zeros, the electrical information flows on a wire. DOCSIS, which is what cable modems use, that's their spec for what electrical voltages on a coax cable represent ones and zeros to your cable modem. And there are also, so I should say, so like these are conceptual levels. A certain standard might take up several of these and might say like, hey, for example, USB has parts of the physical layer, data link layer, and network layer all baked into it. So some specs cover multiple layers. These are sort of perceptual levels of understanding. So RS485, just physical layer. Electrical levels, connection levels, something like that. So what we did here was use, basically, set up a UART over RS485. We had sort of one physical layer spec, if you will, which was this orange wire going high and low. We shoved it into this transceiver, which turned it into another physical layer spec, if you will, which is this sort of RS485 spec that we now know and love, which is now being very sketchy on my workbench here. There we go. Then on the other side, we sort of turned that physical spec back into that original one, right, and turned it back into a UART style voltage going over this wire and into an Arduino, right? So already we're sort of building layers upon ourselves. So with just a physical layer device, you can get ones and zeros from one place to another, but we really don't want to send ones and zeros. We want to send packets or bytes or little chunks of information, and that's what the data link layer ideas are responsible for. So transporting chunks of data directly between two physically connected nodes. It might have ideas built into it in terms of flow control, like who's talking when, like we talked about earlier. Error correction, like do I need to send more bits than necessary so I can check for errors that might have happened on my line or account for noise or something like that, are all the purview of the data link layer. So the UART protocol, with its idea of like what ones and zeros represent a byte, how I'm going to terminate my things, that all makes up part of a data link layer protocol. Other things that show up on data link layer, MAC addresses, so when you connect two devices via Ethernet, they will each have a built-in address, an identifier on the line that says, hey, I'm connected to this copper and I'm called this. I'm connected to this piece of copper and I'm called this, and so on. Those are all data link layer ideas. So with a data link layer in place above your physical layer, now you can have two devices that are directly connected on a wire talking to each other. And a wire being a substitute for wire, fiber optic cable, RF connection, and so on, whatever your physical layer is, right? So for our examples today, that's basically as far as we get, right? Is our physical layer and our data link layer, because all our things are going to be directly connected on basically one set of physical wires, one long copper line. For the sake of being nerds, I'm going to talk about a couple more layers of the OSI model because I think it's a really interesting thing, and useful for sort of like conceptualizing a lot of the concepts that we talk around. So now with our data link layer in place, we can pass sort of packets of data along a physical wire. But what is, if I wanted to send a signal, and this I'm stealing an example from friend Smitty Halibut, so I don't know if you'll ever watch this, but Smitty, credit to you for this example. If I want to say send an email from me to Travis, because you're the last one I'm seeing in the chat. If I'm going to send some information from me to you, Travis, so really what's going to happen is a process on my computer wants to send some data to a process on your computer. We're not connected by a single continuous piece of copper anywhere. What's happening is my computer is hooked in via a cable right now to what I call my Wi-Fi router. That's hooked up to a cable modem. That's hooked to another, a big computer in the cable office at Comcast in my case. They're hooked to some other things, eventually to a wire that's connected to Travis's computer, right? So I need a way not just to communicate within physically connected wires, but I need a way to pass data between multiple networks, between multiple sets of interconnected copper. And that's what the network layer takes care of. So things like an IP address are an idea that exists at the network layer. How am I going to take this data that's coming into, say, my router on one of my copper links? And how do I decide which of my other various copper links or Wi-Fi ports or RF devices or whatever I'm going to do, where does that data need to go? How do I know where to send it? So with the network layer in place, you can sort of get information from one physical computer on one network to a computer on another network. And then above that, we have the transport layer, which is, really I don't want to send information from my computer to your computer, Travis, in this example. I want a process on my computer, my email client, to send information to a process on your computer, your email client. And so the transport layer encapsulates the ideas of sending information from a process within a computer to a process on another. So TCP and UDP are the primary modes of communication. The transport control protocol and the unreliable datagram protocol are the ways of encapsulating data in such a way that it can make it from a, I could have a process on my computer, my email client, sending information to Travis's computer, but Travis could also be using my computer as a web server to download these slides and something like that. We can have multiple flows of communication at the same time. That's all encapsulated at the transport layer. And then, like I say, I think that's where my last slide is, because above that, things get a little bit sloppy and sort of end up in software. So like session and applications, just to be a nerd about it, the session layer is supposed to sort of encapsulate like oh, you're not over there, you're over here. Sort of like long-term persistent connections between two things. That sort of get wrapped up into transport because TCP takes care of that for you. Presentation is supposed to handle like translation between multiple ways that devices can translate data, like ASCII versus UTF-8, but that sort of is all wrapped up into software in the application layer. So really most think about physical, data link, network, transport, and then application, right? And for a network engineer, right, you would be concerned with physical, data link, network, transport, and application is somebody else's problem. As long as the processes are communicating, what happens in them, that's somebody on top of that, right? Questions on that while I hydrate, because I know that was just a bit of a flow, but I think it's super cool. It's a really interesting way of thinking about how you stack ideas on top of each other to establish a communication flow. Let me mute myself again just for the kindness to your ear. Had a little bit of a weird flash there because I still have my radio ID number from work on this water bottle because it was my work water bottle for a long time, and I'm just thinking about work because someday I'll be going back there, hopefully soon. It sounds like, but we shall see what comes up. Yeah, so that's the OSI model. In a nutshell, in a really brief way, and I encourage you to like go and learn more about it from someone who knows more than me because it's a really interesting thing. But this is how the OSI model fits into what we've been talking about today. This labeling is actually not mine. It's a little bit misleading. In fact, maybe just for the sake of posterity, we'll just crop it out. Just a little behind the scenes here. We'll just crop that. We can stretch this out more. There we go. So you can see we have our 7 layers of our OSI model. This is the one this is sort of the mode we've been existing in so far. We had our physical layer, which had our sort of our RX, TX, ground, 0 volts, 5 volts, and so on. On top of that, we had our UART protocol, so how we're translating the ideas of like a byte into a series of ones and zeros on the line, and everything above that we were doing in software. What we'd really like, and sort of to be able to control these two Arduinos separately, or to think about it in reverse, if these were 2 separate sensors, how we would have them, both communicate their data separately to the transceiver side of things. What we really want is a model more like this, that has a physical layer to it. Maybe it's based on UART, maybe it's something like 0 to 5 volts as well. And then it has an addressing scheme built on top of it at this network layer, something that's going to give us some ability to, tell devices in various parts of our network what they are. Now, the example I'm going to use is DMX, which gets things actually a little bit squidgy, because since everything's existing on the same line, you could make the argument that DMX really is a layer 2 protocol, that it all exists at that data link layer. It has a lot of properties in common with a network layer protocol, so I'm going to refer to it as a layer 2, layer 3-ish protocol, but I would accept a beer from anyone who wanted to buy one for me and argue that against me. But some examples of things you could build on top of an RS485 link to give you this extra level of communication. So we've seen UART, right? We've been doing that already. DMX, digital multiplex, is the one we're going to talk about tonight. But just to list some others, Modbus and Profibus are the 2 most common open solutions in automation. A lot of automation solutions are proprietary. Like Siemens developed Profibus, I want to say, in the 80s, but now they have their own like Siemens bus that they use, and there's a couple of others that are sort of proprietary. But these are the more open ones that you can sort of learn about out there. And there are Arduino libraries for at least for Modbus and maybe for Profibus too, if you wanted to go and play with those. But today, because it's a topic near and dear to my heart, we're going to talk about DMX. We finally made it, and we're a real human being 90 minutes in. That sounds about right. But we're much more than halfway through, so I feel like we're doing pretty good. So DMX 512, for those who have not run across it before, and I know a lot of the lighting nerds out there have, but just in case you haven't. The DMX was developed originally in 1986 and has had several revisions since then. The current spec is 2008 DMX 512-A. It's managed by the ESTA, the Electronic Standards for Theater Association, something like that. You can find that spec for free on their website. It's linked in the description and the slides at the end. It's a really interesting read. If you're a nerd, but I am, so it's a really interesting read. It's designed for lighting control, and the idea behind it, just to get a little nerdy, I think I wrote up a blog post about this at one point, but in the 70s and 80s, as computer control of lighting design was really coming out, and this is before my time, I will certainly say, but the story goes, and the history goes, and the wiring goes, that in the original controls, right, so your lighting controls that, say, like my father used in high school, would have been something like a big spank of rheostat dimmers with big handles that you'd have to manually adjust. Each one was connected physically to an electrical circuit, and you were manually, through a rheostat or an auto transformer, changing how much electricity was flowing down each of those lines that these handles were connected to. He has some great stories, I think, and I hope I'm not making this up, but like using big pieces of wood to like push or pull multiple handles at the same time, that sort of thing. As technology improved, the idea got to be like, well, could we do a similar thing, but could we use electricity to make our lives a little easier? What if we had, for example, like a motor connected to each of those rheostats, these big bulky levers, and we had a little dial down on our workbench, say for each of those, or a dial or a slider or a potentiometer that could control the position of those motors, right? Then we could just move little knobs instead of pushing big levers, right? Which is a great idea. The one problem with that is you basically need one control wire to run from each of your sliders or knobs to each of your motors. So in, say, a big opera house, like let's say you had 96 of these big old giant things stashed in a wing up high above somewhere, you would need 96 wires with pretty good signal fidelity running from your control station to your bank of rheostats. And you really only talk about them going in one place. Often you'll see like this, this big bank of motorized things here, and your control console is like 12 feet over on the other wall over here, right? You really couldn't go very far because you needed too much copper. There really wasn't a great way to distribute that control or put the controller anywhere farther away than a single, DC electrical signal could reach. And so through a series of intermediate protocols, they started developing what's now known as DMX, which basically encapsulates up to 512 values into a single digital line. Chris says AMX. We'll get into AMX some other time. That is definitely in my blog post, because Palmer asked about it after I wrote it. So you can check it out there. It's on jeff.glass/blog. You can find it. It's like the 5th or 6th post back at this point. Anyway, this is a long and nerdy story just to say, like, the reason DMX exists is that rather than having one wire per control surface running to these various motors, we have a digital line that is RS485 based, running from our controller to a first device, to a second device, to a third device, and so on. It's standardized on 5-pin XLR lighting connectors because they're sort of different from everybody else. It only uses 3 wires. It's based on RS485. It has a common signal plus and signal minus. That's all you need. The shape of so this is right. So RS485, we said, only defines what is a 0 and what is a 1. To build a data link layer protocol on top of it, we need to start defining some structure to our data. And just for curiosity's sake, here's what DMX 512 looks like. We send between 1 and 512 slots of information over and over and over again. Each one's basically a DMX packet. So we're going to send the value for sort of slot 1, the value for slot 2, the value for slot 3, up to at most 512. Then we take a little break. We're required to take a little break, at least 88 microseconds, and then we send the next packet. Each of these packets has a start bit, has a make after break. It has some data, and then it has some stop bits, so we know that we're stopping. And within each of these slots for data, we have 8 bits of data, which can either be high or low, right? So we have 512 slots for data. We have 8 bits, or 255 possible values within each slot, and that makes up our data packet. Then we take this break, we take this pause, and then we start again. Here's a little closer look at each of those DMX packets. So we take a little break before we start. We send a little information to the start called the start code, which tells us what kind of data it is. And then we send the information for channel 1, information for channel 2, slot 3, slot 4, and so on, up to at most, we have to send at least one slot. We can send up to 512 before we start again. And each one, like I say, has has 8 bits. That gets sent least significant bit first, so the 1's bit, the 2's bit, the 4's bit, the 8's bit, in that order, and so on. You don't actually have to know any of this because it's kind of wrapped up in other applications for you, but if we're going to get into this stuff, we totally should. So that is the basic structure of a DMX packet. Up to 512 8-bit values wrapped up in this way, with a break so the receiver can know when a new packet of data is coming. Nate says, what is MTBF? I'm guessing it's not mean time before failure. No, I don't think so. Where do we see MTBF? Oh, here. I actually don't know what MTBF. I stole this diagram from somewhere. I don't know what that's referring to. Typically you can I thought you could just send your stop bits, and be done. I don't know what MTBF. I don't know what MTBF is. If anyone finds out, let me know. Thanks, Nate. No, it's always good to ask questions, and I will try to never pretend to know more than I do. So within a DMX packet, we have up to these 512 possible slots for data. We often think of this as the address of the data within that packet, although there's nothing inside these packets that's saying, okay, here comes the data for slot 1, here's slot 1, here comes the data for slot 2. It's just a list of up to 512 8-bit packets that come along. Oh, Travis says mark time before frame. Okay. So that would imply that your at the end of each of your 8-bit data sections, at least if this diagram that I stole is to be believed. If this diagram that I stole is to be believed, you would have to basically send your lines back to mark for a certain amount of time before your next data frame, your next data chunk. I'm not 100% sure that that's spec, but interesting. We should go look that up together in the DMX spec that we can all read. Maybe you'll do us like a DMX story time, but not tonight because time. So the idea of sending data down this DMX line is that individual devices on the line can choose, or we can choose for them, to be set to listen, to ingest one or more of these slots of data and take some action based on it. So you can imagine, in our previous example where we had a bunch of motorized rheostats controlling things, we could tell, the computer attached to rheostat 1, listen to the whole stream, because you have no choice to listen to everything, take the data out of slot 1 and make that the position of your motor, right? Make that your dimming value, essentially. And the computer connected to slot 2, connected to rheostat number 2, listen to only slot number 2 and make that your dimming value. Miniature moving light, for example, listen to, say, 3 slots. And the first slot will be the intensity of your dimming, the second slot will be the pan, and the next slot will be your tilt, and so on. So you could have multi-address devices, for example, that can choose to listen to one or more slots in your data stream, essentially, and choose to take actions based on them. In lighting, we often call that addressing the device. We say the address of the device is the lowest slot that it is listening to. There's no reason that you would necessarily have to make a device only listen to contiguous slots, other than the fact that it would be a nightmare to try and combine multiple devices in a single line if they did that, and there's no good reason to. But you could, I'm entirely making this up, but I could see there being a world in which it'd be useful to have devices that only listen to, say, a single DMX address, 1, 2, 3, 4, 5, and 512 or something hard coded for I don't know what, to allow for some specific method of control with an older system. Most of the time, you're working with contiguous slots of data. Chris says uses 5-pin connectors but only uses 3 conductors. Yeah, it's true. So according to the DMX spec, you should always through wire all 5 conductors, and there are provisions in the spec for using that second set of conductors for other things, either for a bidirectional data link or for another stream of DMX data that you could do something with. Almost nobody does this. In fact, you may have seen lots of inexpensive DMX-controlled things, including this tiny moving light, will choose, rather than to make use of the standardized 5-pin connectors, they'll only use 3-pin XLR connectors, because if you only need 3 connectors, why not? And these are cheaper because the sound industry makes them by the millions. And so the cheap side of things starts using, like, yeah, cheap DMX devices often use 3-pin connectors. It's not to spec, but if you really are only using 3 wires, so be it. The original idea was that RDM, which I promise we will talk about, which is a way of lights on a control chain talking back to their controller. The original idea was they were going to use pins 4 and 5. But so quickly, like within the first couple of years, device manufacturers were saying, well, if this standard isn't implemented yet, I'm going to save the money. I'm only going to use 3 wires. I'm only going to use a 3-pin connector. And so by the time they got around to rolling out RDM like a decade and a half later, there really wasn't if they wanted to make it backward compatible, you had to sort of assume you only had 3 lines to work with. So that's the reason for RDM existing on the primary data link in its current implementation. We talked about addressing. Oh, DMX start codes, just a little aside. So at the beginning of every DMX packet, where are we? Where's our start code? Yeah. So we have our start code that precedes all of our channel slots. That just tells you what kind of data is coming in. Generic data like dimming data is most of the data that's coming down the line. Uses the null start code 00. Other codes are manufacturer specific, and you could register them when the standard first came out in the 90s. If you wanted to say, hey, I'm going to use start code D6, and that's going to mean that my Centronics lights, when they see a D6 code, they're going to use the data as calibration data for their mirrors or something. There's only 255 possible values, and they're basically all reserved. So this is kind of a, kind of not a thing you get to do anymore. When you're ingesting data, most of the time you only want to listen to the null start code data, to data that starts with a start code of 00, because that's dimming data. The only manufacturer that really gets you in trouble with this is ETC, Electronic Theater Controls, who's one of the biggest manufacturers of control consoles and dimmers and various things. They use alternate start code DD to communicate per address priority data. Basically, we have sending data down the stream of saying, hey, this is DMX data, and my controller would like it to be at a certain priority level in terms of combining it with other data downstream. So that in theory, you could have a device that was receiving multiple DMX streams and saying, okay, here's my data, and also here's how the controllers would like them to be prioritized in a per slot basis. And the way that you distinguish that priority communication versus the data communication is the priority communication will have this alternate start code DD. What you see in a lot of inexpensive devices is just assuming that all data is valid lighting data, and so when this other packet comes down the line that's meant to communicate something else that really isn't meant to be interpreted as, hey, turn the light on, hey, pan this way, you see like lights flash and twitch and all kinds of stuff. If you ever have flashing LED tape connected to a cheap DMX decoder, that's often what it is either per address priority data or an RDM query packet, which we will talk about, I think. Someday we'll do I will just turn this into a theater stream and we'll talk about like cool theater-specific technology. Try to keep it just a little bit more general tonight, but I do want to talk about RDM at some point because it's cool. So this is the circuit that I'm going to use to demo DMX over Arduino because it may look very similar because it's basically the first RS485 circuit that we built. In fact, it is the first RS485 circuit that we built. Because DMX as a spec is built on top of RS485, it says, okay, hey, your signal levels, your voltage levels, your speeds, use RS485. Here we are. We're going to use that exact same circuit and send DMX over it. Palmer says, are there lights or lighting equipment that have moved from DMX to a network RJ45 only for data connection? So it's a good question for me to answer while I'm setting up this demo. So there are some devices, well, I guess I don't know of any devices that are purely and only like a network-based solution. There are certainly setups and devices that you would primarily use the network-based solution. I'm thinking of, for example, a big rack of 96, 20 amp dimmers, like a sensor rack is the sort of the common brand. You can still wire them up with hardline DMX, but it's much more common nowadays, I would say, to plug them into a lighting network and control them that way. So almost all equipment, I guess and Travis and Lee might know of some. I can't off the top of my head thinking, oh, well, I'm sure there are some media servers that only accept network data. So a media server being a device that would, take and store digital media like a photo or an image or a video clip or a transparency layer that you could use a lighting controller or other software to say, show this image at this opacity, at this rotation, at this time, at this playback rate, multiply that by, hundreds of options and hundreds of clips, and output it out the other end. A lot of those are controllable by DMX, but the amount of parameters that you would need to control it would be so extreme that some of them don't actually have hardline DMX connections to them. You can only control them via a network. I think that's like the only thing that springs to mind. And I think the DMX over a network, which we haven't really gotten to, is like not necessarily the best way to control those. But in some senses, they are still being controlled by like DMX over a network. But yeah, so I think that's the short answer. Is like I don't think there's that much out there that is only networkable, but like a lot of stuff, it's like why would I do it any other way? If that sort of makes sense. What was I doing? Oh, controlling things via DMX. That's what I was doing. So that's gonna plug in. So let's see. So I'm gonna need some new code. Let's come over to the code. This will be the DMX send. Let's just jump right to the DMX knob send example from the website if you are playing along at home. I will upload that to my transmitter, and then I will tell you about it. So this is all going to make use of the Conceptonetics DMX library, which is, again, linked down below and on the Electronics Bash website and in the slides. There are several DMX libraries out there. The Conceptonetics one, which is folks who make some DMX shields for Arduino and stuff, is the best one that I know of, or at least the most reliable one. It's not error-free, but it works pretty well. So you can download that one from SourceForge if you want to play around with it. Let's see. Palmer says, surprised there isn't a lighting equivalent of Dante where you plug all the lights into a network and they're all detected. So infrastructure. So okay, so a couple of good questions here. Chris asks about ETCnet. So let's see. So let's see. There's two separate things going on. So ETCnet is a suite of network control protocols that ETC, Electronic Theater Controls, define and uses internally for their products. One of them is what's called streaming ACN. This is out of the scope of what we're talking about tonight, but we're actually pretty close to the end. Like, we got some DMX demos to do, so I feel good about diving into a little bit of off-topicness. Maybe we do the DMX demo first, and then we dive into off-topicness. Let me show you how to use DMX to control things with Arduino, because that's kind of the meat and potatoes of tonight, and then we can certainly continue to be nerds as we go. How's that? So let me show you how to use the Conceptonetics DMX library, because like if you're out there thinking like I'm going to use my Arduino to like receive DMX and control a thing, or be a little tiny light board controlling DMX, I want to make sure we get to this. So you've downloaded the Conceptonetics library. You've included it in your sketch, right? We've gone to Sketch, Include Library, Conceptonetics, right? I've used this define statement here to define the maximum number of DMX channels. I'm just going to use that and my RX control pin to define a DMX master. So when you're sending things in the Conceptonetics library, use this DMX master class. I've just called mine DMX master. I'm only going to have one. The constructor takes two parameters: how many channels you want to send. I'm just going to send all 512 slots. And the RX enable pin. This comes from the Conceptonetics folks planning for you to use this with their DMX shield. Most of these transceiver chips, and I'll show you, and we talked about this in the Building a PCB episode, one of the things they have is these control pins that allow you to turn on and off the receiver and transmitter, or since one of them is active high, and one of them, you remember from this bar, is active low, you can tie them actually both to a single control pin, and if it's high, the transmitter is active, and if it's low, the receiver is active. So Conceptonetics makes you define a connection point for that control pin. I don't have that hooked up anywhere because it doesn't make sense for these little breakout boards, but when you see this, that's what this RX enable pin is. And then the rest of my code is going to look very similar. I have my LED pin. I'm going to say which DMX slot is this value, is my data going to go out on, is the data that I'm going to read from a potentiometer in a second. And I'm going to define a variable to hold that value for now. My setup is really easy. I'm just going to call DMX master.enable. Start transmitting, please. And then in my loop, value equals something. That's a little redundant. I'm going to do value equals, again, same as before. I'm just going to take an analog reading from my pot, which comes in as 1024 max. So I'm going to map it down to 0 to 255. I'm going to write that value to my local LED just so I can see what's going on. I'm going to use this set channel value function. I'm going to call dmxmaster.setChannelValue. I'm going to say which slot in my DMX packet I want to set and what I want to set its value to. And that's going to go ahead and in the background for us, every DMX packet that comes out after I call this function is going to contain this value in this slot. And then I just said I'm going to delay because I don't want it updating too fast. Again, this is ancillary, but here we go. So did I upload this already? I might have. Let's upload it again. Palmer says, I'm impressed by the longevity of DMX based on its limitations. Yeah, it is very reverse compatible, and that's exactly why. Like, people still have dimmers in lights and various things in their building from 20, 30, 40 years ago, and so that spec kind of has to live on. They're especially considering the cost of some of that equipment and the amount of that equipment, things really haven't been able to leave DMX behind, even though they are starting to incorporate new technologies to coexist with DMX. Let's look at our receive code. And we'll do the receive. So things to talk about later. RDM, ETCnet. We'll put a pin in those. Kenneth, remind me. So on the receive side of things, this will be the DMX receive basic demo if you're playing along at home. DMX basic receive, I guess. I'm skipping the DMX basic send demo because it's not as interesting as the knob demo. So I guess I don't need my servo included here. That's a leftover from something else. I'm including my concept and NX library. I'm just saying how many channels do I want this DMX receiver to listen to. I'm going to define a device called a DMX slave class device. I'm just going to call mine DMX slave. By the way, I will totally say, because we were having this conversation in some nerd communities on Twitter, and it's just worth acknowledging the master slave terminology is very contentious right now, and is changing in a lot of contexts. It is a long-standing term in electrical design, and it's what these libraries use, so I can't help but not use it. There's a lot of other good suggestions out there for what it should be called in the future. So that's where this language is today, and it would be lying to tell you that's not what the language is, but I just want to acknowledge that that's out there. So how many channels does this DMX receiver use? It's going to use just one channel to listen to. I'm going to define a pin to connect my LED to on this device. Again, it's pin 6. And then like before, I'm going to enable my receiver here and tell it what address, which slot it should start listening at. And all of the addresses I'm going to receive later will be relative to this address. So if I start at address 2, then later when I make it a little clearer. If I start at address 57, then later when I say get the value at slot 1, it's going to be slot 57 in our chain. Then slot 2 is going to be slot 58, and so slot 3 is 59. It's all relative to this start address, if that makes sense. My LED pin is an output. I turned it off to start. Again, not necessary. And then my loop is just one function, which is going to say get the value of slot 1 relative to my start address, which let's just make DMX address 1. I'm going to write that value directly, because the DMX value is between 0 and 255. The analog write function takes a value between 0 and 255. I'm just going to write that value straight to the LED pin, right? So again, I'm going to need to unplug the RX pin from my Arduino there before I upload it, and I'll upload that code. Hopefully that uploads just fine. Uploading, and we're good. So let's see. So I think I've uploaded all the code now. So if I plug this back in, then like before, I put those two things both together on screen. Again, modulo some sketchy wiring on this potentiometer, right? As I turn the potentiometer, both things dim in unison, right? So this is reading a value, writing that value to the LED, sending that data over DMX to this side, turning it back into a signal that can come into my receive pin here, and writing that value straight out to my LED there, right? So this is the gist of DMX communication from an Arduino to another. So DMX being generated here, being received there. And this is just generic bog standard DMX. Like, this could be coming in a signal from a light board. This could be a signal like sending to a light. In fact, when I'm like testing my little tiny moving light, I'm using usually DMX generated from an Arduino because I have sort of more precise control of exactly when things are happening compared to like going through a piece of software on the computer. So that is the gist of DMX. So this is, again, we're doing just exactly the same thing as we did with our pure UART RS485 example. What have we actually gained? Well, as we sort of mentioned when we introduced DMX, one of the points is to be able to incorporate an addressing scheme, of course, into our devices. So let's upload some code to our other Arduino over here. I'm going to use the same DMX receive code, except this time I'm going to set the start address to 2. And I will make sure I'm connected to the right port and upload that. And it's not connected to anything right now, so hopefully it will upload just fine. Upload just fine. Not uploading just fine. Maybe I'll disconnect that there. When the uploader hangs like that, I find it's fastest just to unplug the USB from the Arduino and plug it back in. Kind of resets the programmer, and you can sort of start again. All right, so they uploaded correctly this time. Let's take a second on the table off to get this wired back in. Oh, where does this receive pin go? I unplugged it from the place I didn't mean to unplug it from. So receive out is pin 1. So this should go to pin 1. All right, and so get that all up here. Here's my other wires. I'll get this wired in place. I'm really grateful to Past Me for doing a little bit of color coding on the connections on this last board over here. It's alleviating the need to think about too much of this right now, which is helpful. White goes to white, so that's my B- line, and black goes to black. That's my A line, my uninverted signal line. That. Make sure this Arduino has power again. Does. Now, let's see. Why are you not receiving? So let's see. So what's happening? So I've got my first 2 LEDs are turning on. This one is not. What's happening there? Most likely, aha. Well, that would do it. Sketchy connection. What's happening here? So 1. Data out. Those are tied low. That's tied low. That I did upload the code. Oh, I know what's happening. I'm actually sending any DMX data to it. Well, are these circuits relatively protected from shorting? Yeah, they are decently well protected. They can tolerate up to like 12 volts on the input side, so they are not really in danger of me shorting 5 volts to the wrong input now or anything like that. The bigger problem would be if you reversed a power and a ground connection. Like feeding 5 volts into the power and 5 volts into ground is not typically an issue because no current will flow. Reversing them so there's 5 volts on ground and ground volts on the power input is often more of a problem because you can get power flowing backwards to things that shouldn't have power flowing through them. But yeah, other than that, they are typically mostly fine. I'm realizing the issue is I am not sending any data out on DMX slot 2. I have one more example for that. So this will be the DMX knob send dual example. If you're playing along at home. It's very similar to the last example. It's just that I have 2 potentiometers. I was going to wire in 2 LEDs, so why not? We'll do that. Pins 10 and 11. And I'm going to read a value from 2 potentiometers. I'm going to read a value from potentiometer 1 and set slot 1 to its value, and read a value from potentiometer 2 and set slot 2 to its value. So let's do that. Do I still have... I do not. Let's see here. We'll get the LED hooked up first and the potentiometer. So I'm going to hook up LED here. I'm going to need... What's weird is I must have done this. Like I do all of these demos in advance and just prep them, and I have no remnants of this demo. Like I have the potentiometer, but not the second LED. So like, I'm not 100% sure how this happened, but what is time these days anyway? Let me hook up the second potentiometer here. So this will just be to... Yeah, and I labeled this potentiometer to match this demo. I didn't have the LED of the resistor out. Did I not do it? That's okay. This is just the ramblings of a madman who's done 16 weeks of these now. Make sure that's connected to the right place. Looks like it is. Let's see. Did we upload that code? I don't think we did. That would help, huh? We'll select the right COM port. We will upload. There we go. So now we come back to the table. We'll see we have 2 potentiometers and 2 LEDs. When I turn the first potentiometer, you see the first LED dims, and the LED connected to this receiver dims, right? So that's DMX address 1 dimming. When I turn the other potentiometer, you'll see the red LED here dims and the yellow LED there dims, right? So this is DMX address 2. So by building a signaling protocol, an addressing protocol on top of RS485, one of the abilities that we've gained is addressing. Now, of course, DMX is not the only way to build an addressing protocol on top of RS485. Modbus, Profibus, and others are ways to do it. Record Q1, says Travis. Yeah. I mean, you know me, my theory, my master electrician theory of Q building, all lights at 50%, record Qs all go home. But that's just me. So now we have a single controller talking to multiple separate receivers. And that's one of the goals of DMX, is to give us the ability from, a single, say, lighting control console to talk to multiple end user devices. Now, of course, you probably wouldn't wire it like this in practice, but I suppose you could if you wanted to. That is the gist of the benefits of DMX. So just to drive the point home, how this integrates with the OSI model, right? So in our 7-layer burrito here, our physical layer is RS485. Our data link with shades of network layer here is DMX. And because everything exists on a single wire, we don't need the ability to transverse multiple networks, multiple hardline networks, or communicate between multiple processes, because by definition of DMX, there is only one receive and transmit process. Our application layer might be different, right? You might be, might have in my case, a potentiometer and some Arduino. You might have a $10,000, $100,000 lighting control console or system, and right? But that's an application application layer difference. This is sort of how things bake into our OSI model here. Let's see. Where do we mean to go next? So this is the wiring for the second Arduino circuit. Again, it's exactly the same as the second RS485 circuit that we did. Download the slides and look at it if you want to figure out how to wire these up. Gonna use alligator clips to replace all my DMX cables. I did not say that. Those are not my words, and I do not recommend it. So let's talk about RDM. I need to grab some paper and pencil to illustrate this, because I don't have slides on it, but it's super cool. I'm going to talk about RDM, ETCnet, and what we're talking about next week, and I'll get you out before a Jeff Glass 90 minutes is done. Hang on. There we go. I hope that's still right. I don't know why they're alligator clips and not crocodile clips. I think it's because the teeth of a crocodile typically extend like outside of their jawline, and for the alligator clip, that would be a design flaw. So maybe it's a very clever thing, or maybe the original makers had only ever seen an alligator and not a crocodile, or who knows. But it is an excellent question. Let's see. Can we see that well enough? Let me boost this just a little bit so we can see a little better. There we go. So I want to talk just briefly about RDM, because it's cool, and sort of the way it handles multiple things talking on the line at once. So, and I will probably get a few of the details wrong to talk about this. You can go. So actually, I'll show you if you want to, because I always had the hardest ding dang time finding out where to what the different protocols, not the admin page, just the blog, what the different protocols were called and where do I find information about them. I should link this somewhere as well. But I wrote up mostly for myself what the different protocols are, what the specs are called, what their AMX. Yeah, so I wrote a post, I guess February of last year. God, that feels like 1,000 years ago. ANSI E120 is RDM. And the RDM spec, which you might as well leave up. Let's see. ANSI E120. So we can reference it. Oh, yeah, they want you to buy it, but I'm good. I want to pull up ANSI. So you go to the TSP page on ANSI's page. You can read the whole spec. I'll enter my email. which is fine. Probably fine. Probably not great to enter just like on a general stream, but that's all right. I'll blur that out later, maybe, if I feel like it. ANSI E120, yes, remote device management for DMX 512 networks. So, what RDM is doing is based. So each device has a 64-bit name that consists of a. I'm not going to guess what the bits are, but it basically consists of a manufacturer ID and a device ID. So basically, when you want to start manufacturing devices that are RDM compatible, you sign up for a manufacturer ID. Let's say it's going to be like, I think, a 16-bit hex number. Let's say mine is OOX ABCD, right? So I have 16 bits of that. I have a 48-bit device address. So it might be OX, might be ABCD, ABCD, ABCD. And the idea is when you make devices, every device that your factory makes has the same manufacturer ID, and every single device you make ever has a unique device ID. So when they roll out the assembly line, it just increments by 1, or is randomly assigning checked off of a list or what have you. And in this way, you have a 64-bit number, which is has 2 to the 64 possible values, so that every RDM device in the universe will have a unique address. So every device has its own name that it calls itself. And so, in sort of a basic way, like the sort of standard bit of RDM is the RDM, much like other RS485 talkback protocols, has a methodology for the lighting console to reach out to a specific device on the network and say, hey, I would like, let's say I have my lighting console and I have my first light and I have my second light, right? There's a command for the lighting console over what looks like a DMX message with an alternate start code. I believe it's like 1D. I might have that wrong. 0D. To say, hey, light 1, please set your mode to this, or set your calibration to that, or please send me back the measurement on your heat sensor or your motor current or something like that. And in the RDM spec, there's lots of defined values for the various things that your RDM controller is allowed to ask about, and the values that your lighting device will send back. So this is just a random page here, but in response to the question, what kind of lighting device are you? Your device might send back, I am a device type OX2000, no fine category. Oh, I have a OX2002. I have a moving yoke. I have an effects disc, something like that. So there's all kinds of sort of standard things that your lighting controller can ask about. Various details, multi-channel, how you change over to failover equipment and various other things. Please strike your lamp. Please turn off your lamp. For lamps that need to be manually ignited with a ballast, essentially. So this is all relatively straightforward. We don't need to get super into the details, but you can imagine sort of a message flowing down the line saying, hey, light 1, please send me your temperature sensor data, for example. The lighting console turns its transceiver off. The LX1 turns its transceiver on, and right back down that same line sends a specifically formatted message that says, this message is meant for lighting controllers. The data is that my temperature sensor says X, right? And so any other device in line is going to say, hey, that's a message intended for the lighting controller. I'm just going to ignore that. I should ignore that. Like I say, lots of devices ignore that initial start code that tells you it's not just a generic lighting data message, but in theory, they are ignoring any data that's not that. So that's the basic part of RDM, right? Sending messages back and forth. The cool part is how RDM actually finds devices on the network. So in like a Modbus or a Profibus scenario, what you would do, let's say this is Modbus. I'm not an expert on Modbus, but from the little I have touched it and from what I understand, right? If this is like you're setting up, a bunch of motion sensors around the outside of your robot that's welding a car together. And if any of them trips, you want to shut that robot down. So I've got 8 motion sensors. I'm not going to draw 8 things. I've got 2 motion sensors set up around my robot. I have my central controller, and I have my various sensors, and because they're RS485, they're daisy chain. For industrial applications, it's not necessarily uncommon for a single controller to have multiple RS485 inputs and outputs. So if, for a controller that's meant to take in a lot of data from a lot of different sensors, you might have like 4, 6, or 8 different RS485 Modbus ins and outs. Let's see. Can RDM change the address of a light, says Chris? So it certainly can. So what it will have is a permanent 64-bit ID that uniquely identifies that device, but the DMX address will just be one of the parameters that it has. So you could send a message that says, change the DMX address, and tell me the DMX address that you are, and the light would would change its DMX and send the DMX address back. So the DMX address of the device and the RDM address of the device are, in some sense, are different sort of things. This is baked into it by the factory. This is something you can set from, any system that can act as this lighting control software. There's, not a lot of devices have implemented this like direct feedback option. But more are coming. Part of the issue is that there's a limited number of devices where that level of feedback is useful that aren't also already on a network. Palmer asks, is DMX bidirectional? So DMX in and of itself is not. DMX is just, according to the spec, according to the primary aspects of the spec, DMX flows from a controller down a line to end user devices. There are, like I say, in the appendices, various provisions for bidirectional communication on a second pair of wires, and RDM, in very many ways, is that level of, it basically is the bidirectional part of DMX. So DMX, 2008 as spec said basically hey, here's how you send data one way. Later on, maybe we'll tell you how to send data the other way, and that's basically what RDM is. It implements this level of how you communicate on a single pair of control wires, this back and forth of, hey, I'm talking now, you talk next, and so on. Where was I? Oh, discovery. So Modbus has a system. RDM is on top of the DMX wiring, and that's partly why it's so cool, right? You don't need any additional wiring. You can use, if you have a lighting controller that's RDM enabled, you don't need any additional wiring to control over RDM. Now, if you had one of those splitter devices in line, an opto-ISO like we were talking about, a lot of them, be like a whiteboard. A lot of them will be, so let's say you have a situation where you have an LX console going to an opto, going to, multiple lines of DMX out with various lights at the end of them, right? A lot of time for less expensive optos, this is a one-way system, right? It's looking for signals here, it's duplicating them and regenerating them here. A lot of them, especially before RDM was a thing, why would they, don't have the provision to listen for signals here and send them back the original way. The more modern optos and the more modern gateways do have that functionality, but a lot of the less expensive ones don't. So this is a situation where even where you have RDM, you need an RDM compliant splitter, opto-ISO splitter, to be able to take signals back in, sort of going the other way. But to get back to discovery, because it's cool. So Modbus, right, another RS485 based, communication thing, 2 wires, has an addressing scheme. We don't need to get super into the weeds, but basically it has a way for each device to have an address, much like a DMX address, right? So let's say this one's address is 4 and that one is 7, right? I think they're 8-bit numbers, but let's say they're 4 and 7. In a lot of Modbus schemes, you would have to go into the control software on this device and say, hey, your sensors are at 4 and 7, and I'm going to hard program that in, and it's never going to change. Because this is meant for applications where things don't change, right? Like on a factory floor, or at least they don't change often. And if they do, there's a qualified technician there with his laptop or his terminal when this stuff was invented in the late 80s saying, here's the hard-coded addresses for all of this stuff, right? RDM does something really cool because it's meant to be used in applications like stage shows, theater, touring stuff, where you're plugging stuff in, plugging stuff out, and you're expecting that the controller is going to be connected to different things a lot of the time. And we don't want to necessarily refer to devices to communicate with purely by their DMX address, right? Because multiple devices in the same line could have the same DMX address. There's nothing wrong with that, right? You could have going back to our dimmers example, even though they're not driven with motors anymore, you could have two devices listening to the same slot of data, or two multi-parameter devices, that might need to always be doing the same thing. They could be listening to the exact same slots of data. So using the DMX address as the address of who I am the controller talking to is not great. That's why they have this sort of unique 64-bit ID, so we always have a unique name to call things. But how are you going to figure out what those names are without hard programming them into your lighting controller, right? How am I going? It'd be a real pain to say, all right, I've plugged in, 30 lights on the balcony rail on a point-a-minute thing, and now I have to enter 30 64-bit addresses into my computer so I can control them. So RDM does this really nifty thing. This is what they recommend you do. You don't have, this is a suggested part of the spec, not a mandatory spec. But it basically says, this is all done in a 64-bit address space, right? I'm going to do it in a 16-bit address space just to make the writing a little bit shorter, but the example is exactly the same. So just when I'm using 16 bits, you can assume this scales up to 64 bits. Lee says, have you ever met a designer who is good with movers address the same? Only long ago in storefront when you might only have 512 addresses to play with, and some cheap moving lights. But that's for our horror stories night when we hear more about frying a bunch of RS485 chips. Not Lee. It's Lee wants them addressed separately, maybe addressed twice. So I'm gonna do this example in a 64-bit space, 16-bit space. Just know it's really in 64-bit. So in a 16-bit space, right, our possible 16-bit values in hex are OX0000 to a maximum of OXFFFF. Right? That's how 16-bit numbers show up in hexadecimal, right? Which you remember is just a shorter way of writing in binary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And those are all zeros, to binary 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? Same thing, just a shorter way of writing the same thing. So we're going to just do this all in hex. So the first step in the RDM discovery process, this is a process of you say, all right, I've plugged a bunch of lighting devices into a standard DMX line, just 3 wires. I want to know what their RDM addresses are so I can start talking to them and asking them what they are and what they can do and what their DMX addresses are. So the first thing it's going to do is say it's going to ask the whole line, anyone from addresses 0 to all, 0 to FFFF, please come back to me. It says, please, hey, if you have an address, if you have any address at all, say here, basically. Tell me your address. Say hi. And there's a specially formatted response. It's a pretty lengthy response. It's actually a lot. Rather than saying hi, it's more like saying, hi, I am a light, and I'm talking, and this is what I sound like, and my address is 100100110, on and on and on. If there's only one device plugged in, that's where we stop, right? So let's see. So if we can understand the address, right? If we understand what's being said to us, then we can sort of stop, and we know that that's where our one device in the network. Totally easy, right? What the other scenario is that we get gobbledygook, right? If we have 2 or more lights talking at the same time, the message that's coming back is going to be incomprehensible, right? Because the ask is not just, it's just like, hey, any light that you have in the network, just say hi. And if you have even 2 lights, let alone 50 lights, saying, oh, I'm this light and I'm that light, oh, it's all going all right. What you get back is a message that is just that is not parsable as an understandable message. And the way that these responses are formatted is specifically so that when they start colliding and overlapping, they are unlikely to collide in such a way that yields an intelligible message, right? What's a good analogy? It's like saying, hey, every light in the system, I'm gonna lay you out a Scrabble board. Throw me back the letters of your name. Right? If you have 1 light and they throw you the letters of their name back, you will be able to read it. If you have 20 lights all throwing their letters on the Scrabble board, it will be incomprehensible, right? So, assuming you get an incomprehensible answer, we go to the next step, which is we first ask about half of the network. We say, all right, any lights with addresses in the lower half, 0000 to, let's see, what would half be? 7 FFF, right? We take away the highest possible bit. Please come back, right? And again, if we understand, we stop. If we don't, we cut it in half again. We say, all right, anything from 0 to 3 FFFFF, please come back, right? And we do this until we get just a single response, right? And we verify that's actually what the light is. We're also going to need to sort of go down the other half of the tree. So lights with addresses from OX8000 to OXFFFF, right? Please come back. And if we get a positive response, then we stop. And if we don't, we basically bifurcate our way. We sort of do a binary search down the possible address space. That sort of makes sense? So we start with, just to list the possible addresses, right? Assuming we get invalid responses at all these steps, where we start at 0 to OXXF, then we branch to 0, 1, 2, 3, 4, to 7 FFF, and 08000 to OFFF. Right? And then if we don't get any responses there, we branch again. We do basically a half of that range and a half of that range and a half of that range and a half of that range. And we go down and down and down until whatever branch we're in only has one response. And then we continue with the next branch until we're done. So, and the clever thing here is not only like, this is a relatively efficient way to search through a possible address space that is in the 2 to the 64th range. So like 10 to the 20th. So what is that? Billions of trillions of possible addresses. It's a relatively easy way to find the 50 lights that are buried in there. But also the formatting of this message, the way that they've sort of constructed it so that, like, you know, you can imagine if the messages were short and easy, then you might get 2 lights sort of talking on top of each other in a way that makes them look like a third light. It's really unlikely for that to happen because of the clever way that the lights are constructed with each other. So that's the neat bit about RDM, is it allows you to hook up a bunch of lights in a chain, run this discovery process, and then your controller can say, all right, well, I found, you know, this 64-bit address and that 64-bit address, and I can start asking them and saying, cool, hey, so, okay, I see you're there. What are you? Oh, you're a color source spot, or you're a dimmer, or you're something that Jeff Glass made up. Like, what the hell are you? Chris, how long does that discovery take? Not long at all. I mean, it can depend on how many devices are on the network, but, like, for a practical system, a few seconds, right? Because at most, you're going down 64 levels down this chain. If you had devices, I'm just going to use all the paper. If you had devices with address in a 64-bit space, 0, 0, all zeros, and 0, 1, you would have to split, and this would be impossible, one, because if device manufacturer 0 doesn't exist. But right, if you device manufacturer 0 has their 16-bit address, so 0, 0, 0, 0, 0, right, that's their manufacturer ID, and this is the first 2 objects off their assembly line, right, which are 0, 0, 0, 0, 0 and 0, 0, 0, 0, 1. You only have to go down 64 steps down that branching tree until these 2 no longer collide with each other. And you can do 64 steps of that tree pretty fast, because these messages are not coming in terribly fast. It occurs to me, I never mentioned how fast a DMX stream is. A DMX stream is based on RS485, and it is specifically a 250 kilobits per second RS485 stream, which is middle of the road as far as RS485 speeds go. You can push RS485 up to, like, 10 megabits per second, like I say, but for a lot of practical purposes, 250K or maybe 1 megabit is sort of the fastest that seems to be in the wild. Chris says, when does it get to the point that we are ignoring DMX addresses and just transmitting the parameters to the 64-bit address? So there is a really interesting proposal that's sort of making its way through the manufacturers right now, whose name escapes me. Travis might know. Lee might know. Any of you might know, but Travis is the one who leaps to mind. It's an interchange format that is meant to make it easier to exchange information about lighting devices between control consoles, drafting software like Vectorworks and AutoCAD, and the devices themselves, to have like a unified identifier, like an idea of like a light could have the same representation of itself as the console or the drafting software would. And at that point, GDTF, yeah, that's I think what I'm thinking of. Yeah, I honestly don't know much about it since like the press releases came out last year. So So maybe, Chris, I mean, really that day will be when we throw out all of our DMX hardware. So never, I think, is the true answer. We are, getting to the point where within certain limited ecosystems, it becomes less necessary to know what the address of everything is. And certainly, like, there are improvements in workflow, like, for example, at Chicago Shakes, where I used to work in the yard, what our typical habit, like, I used to make DMX maps of every plot before we loaded it in. Here's the fixture, here's what its address would be, here's the universe, here's where the DMX goes. And by the end of our time in the yard, because everything's RDM compatible, I would just say, all right, as long as, here's our DMX node, which we haven't talked about, it occurs to me, make sure all of these lights of these various, here's where they go, here's where the designer wants them, plug them all in this chain, and we'll just address them later via RDM. Like, I'm not going to tell my technicians to actually address them anymore. I'm just going to say, hey, I'm going to have the console identify what lights are on here, and I'm going to just, there's a, basically a functionality that says once it's identified all the lights, you can start doing things to them, setting DMX address, but a really common thing is to say identify, which is up to each light to implement, but it often just means, hey, flash at me. I'd have this one flash, and I'd say, okay, well, that's going to be, address 1, and this one's going to be address 2, and 3, and 4, and so on. It becomes less and less necessary. So yeah, general device type format. So it's possible we're moving there. I just have to think, like, though it will be a useful add-on to what we have until we can throw away our DMX devices, which nobody can. I mean, especially now. Like, it seems like we are stuck with DMX addresses forever. As long as we're talking about DMX, and these are things that I think most of y'all already know, but as long as, like, this is going to be like, I think probably not my only time talking about DMX, because nerd, but a couple of other concepts just to mention, as long as we're defining things. So I'll just use more paper. See, these are things that all could have been slides, but they're kind of more fun to draw. The concept of a DMX universe, right? So each line of DMX has, I said, 512 possible slots of data moving down the line. What if you need more than 512 possible slots of data? What if you have, 700 dimmers? Or what if you have, a moving light might take 10, 20, 30, 40, 50, 100 parameters, pan, tilt, positions of various color wheels, various zooms, various ways of dimming, the shutter strobe. Some parameters might take 2 slots. I might need 16 bits to define really specifically where the pan and tilt of a device are, and so on. How are you going to get more control in your system than 512 bytes allow? You just start adding additional lines, right? So I have 512 bytes of data coming out of one place in my control software, another 512 coming out somewhere else and going to some other devices, another 512 coming out somewhere else and going to other fancier things, another 512 coming out of other devices, and so on. The common way to think about these is to say that each one of these exists in a separate universe, a separate full set of wired connections, right? So, and often in many systems, they are numbered. In older systems, sometimes you'd see them lettered, but often we would, give them a more or less arbitrary, say this is universe 1, universe 2, universe 3, universe 4, and so on for however many sets of outputs that you have. And then it's the common notation, at least in ETC land, is to just denote that by a slash, right? So I would say that if there's a light out here that has address 47, so it starts listening to data slot 47, I might say this exists at address 1/47. So universe 1, chain 1, address 47. A device down in this scribble here, which might take 100 addresses, but starts at address 201, I would say this one has address 4/201 because it's in this physical line. This nomenclature, of course, starts to become important when we talk about networked DMX, and this kind of... Oh, this goes back to ETCnet, which was that other thing that we put a pin in. So ETCnet does a few things, one of which is called SACN, which is basically a light... Is that Demi-Light in Universe 4? Yeah, the Demi-Light takes 100 addresses. It's doing its dimming in a space that's larger than the possible states number of atoms in the universe, because that's how much time I've... No, it's fine. So the SACN, or Streaming Architecture for Control Networks, is a lightweight wrapper for DMX. It's basically a way of saying, DMX data at its core is 512 bytes of data coming down a line. Slot 1, slot 2, slot 3, and so on up to 512. Let's take that and with as little preamble as possible, wrap that up into a UDP packet, right? Going back to our OSI model, right? So I have my idea of my data here, and rather than shoving it down an electrical line, I'm going to wrap it up in a UDP packet and shoot it as fast as I can over a network to a device on the other end, which will either just take this data and use those 512 bytes to do something with, or, just so we maintain screen direction there, it might go into a DMX node, which takes that data and turns it back into regular old 5-pin RS485 DMX to go out to various lighting devices, right? So a DMX node it could mean many things. It's kind of an overloaded term, but it typically means something that takes networked DMX, of which SACN is just one form, and turns it from the idea of a networked protocol into a hardline DMX protocol. Now, of course, you could be shooting, not just one universe, not just one set of 512 bytes of data, but multiple sets of 512 bytes of data over your network at the same time. So I could have data for universe 1, data for universe 2, universe 3, and so most nodes, I say all nodes, have a configuration possibility. You can say, hey, I want you to listen for a UDP packet that's tagged with, say, universe 3, and turn that universe's worth of network data into hardline DMX here. They might have a second port that says, hey, I want you to be configured to universe 2 and set your data to somewhere else, and so on. This also opens up the possibility you could have multiple network nodes scattered throughout your building, right? And some of them could share universes, right? This port could also be configured to say, hey, the lighting console is putting out over the network these 512 bytes of data tagged with universe 3. I want you to also spit out universe 3 as regular old hardline boring DMX to your fixture. So universe 3 could exist in multiple places. Let's see. Audio departments have thrown away most wireless equipment twice. Yeah, audio is a different beast. Lighting kind of standardized the thing and stuck with it hard. But Chris says, could you take UDM and turn it into DMX with an Arduino? What do you mean by UDM? UDP? Like ingesting SACN and turning it back into DMX? Yeah, Yeah, so just to be clear, so UDP is the form of the packet. So to go back to our OSI model, yeah, I knew this would pay off. Go back to our OSI model. Where are you, OSI model? There you are. So in the situation where we're sending DMX over a network, right? An Ethernet network, right? Our physical layer might be 1000 base T gigabit Ethernet. Our data link layer has, is the Ethernet layer. It's actually the Ethernet spec. It might have an IP address baked into it so it knows where it's going. It's wrapped up in UDP packets, but the data exists up here at the application layer. The actual, bytes of information are going from one application to another. So SACN really exists as an application layer protocol that is meant to be built on top of UDP. I think actually might specify UDP as a layer 4 protocol, which is often on top of IP, on top of Ethernet, on top of 1000 base T, if that sort of makes sense. So there are other ways of encapsulating DMX data into various packets. ArtNet being the other popular one. So, and Chris, you reminded me we haven't really gotten to the core of what ETCnet is. But so ArtNet is just another, one of the things it can do is another way of wrapping up these 512 bytes of information in each universe into a lightweight Ethernet packet, basically, and shoving them over the network. They do it in slightly different ways. They come from different people. They have slightly different goals. ArtNet has some other kinds of control packets as well. But they're basically ways of shoving data over a network. As far as turning an Arduino into a DMX node, certainly for the right kind of Arduino, it would be possible. The only reason I'm being a little bit cagey about that there is I don't think, and I might be wrong, we have to dig into the library. So with the limitation you would run into in terms of using like an Arduino Uno, for example, we have not talked about timers yet, although we will next week. A timer, so basically inside of the microprocessor are a small number of counters which count basically up automatically over the course of time. In the Arduino Uno, you only get 3. You get timer 0, timer 1, and timer 2. Timer 0 and timer 1 are 8 bits. Timer 2 is a 16-bit timer. And they count upward over time, and you can do things with those counts. They form the basis of like the millis function, does some math on one of these timers and returns how long, and stores some data as well. Doesn't just look at a timer, but it uses one of these timers and knows how fast the Arduino is running and does some counting and does like the millis function. The servo function relies on these timers really directly. It says basically, hey, every time one of these timers passes a certain value, turn a pin on or off. And based on how fast we've made this timer count, we can generate those, 1 to 2 millisecond pulses that define servo rotation that we talked about back in early April, right? So a lot of additional functionality that you can bake on top of an Arduino is going to rely on some kind of precise timing, and is often going to need a timer or two to bake that functionality in. What I don't know is if Ethernet functionality, or to be honest, like the standard Ethernet libraries and chips that you would tend to use with an Arduino, or like in a Shield form factor, if you would run out of timers. You probably wouldn't run out of program space or SRAM or anything, but you might, like this is when I'm trying to make things work together, this is the thing that I run into most often. In fact, if you remember last week, when I was doing that demo that did the turn a knob on this Arduino and wirelessly a signal went over here and turned a servo on this Arduino, I had to do some modifications to the servo library because of the timing of the wireless signal library. It was using timer 1 to sort of like remember when it needed to check in and like update its bits, and the servo library was also using timer 1 by default. So like they were both trying to use this and use its internal functionality for the same thing, and it was causing a conflict. So I was able to move the servo library, it was not a terribly hard thing, move the servo library to timer 2, and that allowed both of them to coexist. I don't know if you'd run into a similar issue doing Ethernet and DMX at the same time on something like an Uno. You certainly can do Ethernet with Arduino, and you can do Ethernet with SACN specifically. Travis and Lee and I have actually done that project. We built a device which basically read an SACN value off of a network. So a DMX value from a universal address you gave it and displayed it on a little LCD screen as a little spotlight display. So some spot ops who had both local and remoted control of their spotlight level could see what level they were at, even though they didn't have a direct physical readout in front of them that told them that exact level. So you can do Ethernet, you can do DMX. Can you do both on the Uno? I don't know. You might need something a little bit beefier. I mean, you could buy a Mega and put you'd start to run into maybe some conflicts. And partly it's like, our libraries that are built for Arduino sometimes reuse the built-in functionality of the hardware to achieve certain things. Like, for example, the Arduino DMX library not only uses timer 1, but actually abuses the serial code, uses the serial hardware inside an ATmega328 to get it, to basically to generate or receive DMX. And that's because the ATmega has built-in hardware to help it handle specifically serial, has UART hardware in it, and so it does that very well. And so the DMX library basically says, I'm going to remove the ability to actually be a serial console, and I'm going to do this other thing with your serial hardware that makes you receive or send DMX, which is very clever. It also, and it is not the only way to do it, that's just the way that I see it done most often. It does mean that for like debugging things, especially with like this Conceptinetics library, you don't have the serial console available to you, because it has been clobbered by the DMX library. Sorry, just checking to see if anyone had texted me, make sure that my comments hadn't died again, but I don't think they have. Palmer, if you can hear me, say aardvark. So a little tiny sidebar on ETCnet, and then I want to share with you what we're doing next week, which I've already hinted at, and then we'll get y'all out of here. So ETCnet is basically, thanks Palmer, it's basically SACN at its core, so start your DMX, and also a suite of proprietary protocols that ETC uses to communicate between its own hardware. It's kind of the boring answer. They don't make public what that spec is. There is in public review right now a thing called RDMnet. So if SACN is a way to send DMX over a network, right? You can imagine that there might be a way to send RDM over a network, sort of bi-directional communication. And it turns out that translating this idea of who's allowed to talk when on a physical wire doesn't have an obvious extension to a communication protocol like networked Ethernet, where the model is not taking turns communicating, but is constant, ongoing, and multiple sessions of communication. And so the bridging of those two worlds, the hardwired RDM world and the networked RDM world, is actually non-trivial. So things like, all right, so let's say I have a DMX node that's taking in DMX and RDM, and I have a master on that line that's sending, messages to various devices on that line. How does that DMX, when that master console tries to discover all the other devices connected to the network, what should they do? Especially if they're multiply connected. How do you define, if you have multiple masters in a network, who gets to be in charge of who communicates on the wired networks when? So if I have two masters on two separate RS485, two separate DMX lines, totally fine, but if they happen to be networked together, and this master says, I want to initiate discovery, A, what do the devices on this line do? And B, what should this master do? It's non-trivial. So RDMnet is the public spec. It's been in review for ages. It's a fascinating read and a little bit opaque. But that is the protocol that basically is trying to define like how all of that handshaking should work. So hopefully we'll see like a public RDM over the network spec sometime in the next couple of years, I would think. The draft spec is out there, and there are some draft implementations. One of the software engineers at ETC actually put out like a draft implementation of the spec, but it's not anywhere close really yet, I don't think. So, bit of a bummer. So that's ETCnet. Some secret stuff and hopefully some stuff that'll be public kind of soon. Why don't we talk about next week and then we'll wrap because it's just been another night now. But I love it. I love these nerdy diversions, and I love talking about DMX. I spent 10 years working in theater, so I love talking about these lighting protocols because it's a whole lot of fun for me. So next week, let's get to it. DMX we talked about. Next week, we're going to talk about interrupts. It'll be a lot of fun. So interrupts, this is a topic suggested by Brian Q, which is a really great one to talk about. An interrupt is basically a way of telling your code in a very low-level primitive way when this pin changes level, or whenever this pin goes low or goes high, or when one of these timers hits a certain value, I want to run some code right then. That is, and I want to do a short bit of code. I'm going to do something, and then after that code is done, I'm going to send you right back where you were. So I could be in the middle of my loop and the other function. I want to come back and I run this interrupt code right at that moment. So that could be a pin changing. It could be receiving something on a serial line, or finishing sending something, or finishing writing something to the EEPROM, which is permanent memory. It's a really powerful way of giving your code the ability to jump around and jump out of itself a little bit more and respond to events in a more somewhat more intuitive way, honestly, than just sort of like constantly sort of looping and checking things. It's sort of the next evolution of this metaphor that we came up with so long ago of like, when did I last check on the baby? How long has it been? I should check on the baby now, right? Interrupts are basically the equivalent of saying, I'm gonna make that baby cry every hour on the hour, and when that baby cries, I'm going to stop whatever I'm doing and go address the baby, right? That's the powerful idea. So that'll be our topic for next week, is to talk about interrupts. We'll probably talk a little bit about timers as well, which I think will be a really fun thing. Here's an important thing to tell you about next week. Next week's stream will be on a different date. Next week, we will be... I've done 16 weeks on Sunday nights. Next week's stream will be Monday night, July 6th, at 7 p.m. Central Daylight Time, same time as all the others. The truth is... my dog, you may have heard earlier, is not a fan of fireworks, and with it being the 4th of July next weekend, we are getting out of town for a couple of days to a cabin in the woods. Make my baby cry every hour on the hour. Yeah, maybe it's not the best T-shirt I've ever come up with. Less than ideal. But yes, so next week will be a day later. It'll be Monday, July 6th, because I don't know that we'll be back in town on the evening of Sunday the 5th to make that happen. And I think my dog will be just so much the more happy about it. She is not super fun. No, she is super fun. She is not having a lot of fun. with the fireworks and the thunder and things. So we're gonna make sure she gets out of the city and gets the peace and quiet. For those of you who know Chicago, we live about a block from Winnemucca Park, which is a big, beautiful park where people set off fireworks from about 1 in the afternoon to about 2 in the morning every July 4th. And we're gonna get her way away from that, I think. So that will be great. So the 555 timer chip is a slightly different thing than a timer inside an Arduino, but we can certainly I can at least share with you what it is. I'm sure I have one somewhere that we could set up in Blink. Maybe that'll be like the pre-roll when things are waiting next time, is a little 555 blinker chip. That'd be fun. I would have a good time. Yeah, that would be a good time. I think that is all of the content for this evening. Here's the business. As always, thank you so much for joining us on these lovely Sunday nights. If you haven't already, feel free to subscribe, and you'll make sure you get a notification of whenever these things are, especially if they change. Like next week, it's going to be Monday night, so don't show up on Sunday night because I won't be here. You could show up, but no one will be here. If you have questions, comments, issues, concerns, please feel free to leave a comment on the video or find me on Twitter at JeffersGlass. All the slides from tonight are at jeff.glass/electronicsbash. I don't know what else. Y'all are great. Please stay safe out there. Please keep washing your hands. Please keep wearing a mask. Please keep being good to each other. I hope you, like me, are finding the strength out of these evenings. Like it is a privilege to unhook on these evenings, and I'm so grateful for it. And I hope it's giving you the strength to go out and change the world and make it a better place. Y'all are great people. Y'all are tremendous nerds. I'm always delighted by like how late it gets and how many tangents we go on, and just like it is truly a delight to do these things, especially to do them here live with y'all is a joy. So thank you. Have a wonderful week. Smash that like button, subscribe. Don't do that. I'm gonna go finish my beer. Y'all should do the same. Don't forget to hydrate. Be good to each other. I'll see you next week.